staffed until the dinner starts at 6:30. So I guess if you want a beer, OER is paying for that. So, yeah, a free beer, a free beer. So we have a lot of engineers in here, so the word free and beer. There's another Raspberry Pi CFS session going to be for tomorrow, starting at 1:30. If you haven't signed up for it, you can sign up for it at the registration table outside the door there. So raffle tickets. We're going to raffle off the MathWorks bag right here. Compliments, of course, of MathWorks. The ticket is 135. Last three digits is 135. Nope. All right. 138. 80. I was higher a minute ago. 74. 121. Well, this is not going to be very. 139. 139. 84. 126. 82. Hey! That's an accomplishment. Thank you. I'm not going to attempt to do another one. Not right now. So we have a keynote this morning, Mr. Larry Leopard from Marshall Space Flight Center. So Larry Leopard is the Director of Engineering Directorate at Marshall Space Flight Center in Huntsville. He leads an organization of more than 2,300 civil servants and contractor personnel responsible for the design, testing, evaluation, and operation of flight hardware and software associated with space transportation, spacecraft systems, science instruments, and payloads under development at Marshall. He was appointed to the position in December of 2018. Larry joined NASA and Marshall in 1990 and has supported a variety of NASA programs and projects. Since his appointment to senior executive service in 2008, he has held, which is, people who know about government, that's like the upper management position. He has held several leadership roles within the Engineering Directorate. Most recently, he has been Deputy Director of the Engineering Directorate. His early work at Marshall includes contributions to the Space Shuttle propulsion elements, the Space Shuttle main engine technology testbed, rocket-based combined cycle propulsion technology, fast-track 60K engine, which was about 10, 15 years ago, International Space Station payloads, Space Station environmental control and life support systems, which is what we saw yesterday on the tour, and research facilities, small satellite technology demonstrations, and multiple science instruments. So this is everybody who works in the Engineering Directorate at Marshall works for Larry. So please welcome Mr. Larry Leopard. You're welcome.
Let's see if this thing works. I can hold it, okay. That may be the best thing to do. Good morning, good morning. Okay, I think that works. Okay, hey, good to be with you guys this morning, and welcome to Huntsville. I think you guys are on day 3 here at your workshop, but I would like to give you a late welcome to Huntsville, Alabama. And some of you, I'm sure, didn't think you would be seeing snow this far south, but we're glad we could bring you a little snow and some ice, which gets a little treacherous around here. We don't have quite the equipment to remove some of the stuff that some of you folks do in the areas that you're coming from. But we are glad that all of you actually have traveled to Huntsville this week to participate in this workshop I personally think events like this are great, where you can get together with colleagues and share ideas, see what other people are doing in your particular line of work. And we are very happy at Marshall to be able to host this event along with the other partners, host partners. And so we appreciate all the folks that have done the planning for this event, and for all of you folks for traveling here to Huntsville. Um, from looking at the agenda, it does look like the last couple of days have been very interesting. I think y'all got a lot of more technical presentations that you're going to be hearing through the remainder of the conference, and I'm sure you'll be getting a lot of that. I also understand that at least a large portion of you got to go out to the center yesterday and got to tour some of our facilities, our system integration lab. And Scott, did y'all get to tour the thrust vector control lab that was adjacent to the facility? Okay, great. And then understand maybe you're in the ECLIS area and POIC. Okay. Oh, friction stir weld. Oh, okay, great. Yeah. Oh, yeah. So while you were there at the ECLIS building, you went over and saw that. Okay, good. Well, I'm glad y'all got to see some of that. We're obviously doing a lot of work at Marshall and a lot of different work, most all of which involves software in some way, right? Shape, form, or fashion. I know this workshop is primarily focused on flight software, but a lot of ground software that's important to, of course, checking out flight software, which I'll talk a little bit more about in our SEAL facility, and hopefully y'all got a good tour. Who actually did the tour for you in the SEAL? Oh, Paul. Okay, yeah, Paul does a good job on that. So he probably told you a lot more than I can tell you about it, I'm sure. But anyway, before I actually get into these charts, I've just got a few charts that we'll use today. But I just really wanted to say I love software development groups. And I haven't always been able to say that. It was, I guess, I don't know. I guess it's been about 8 years ago now. I kind of grew up in the propulsion hardware kind of area. But Tia Ferguson, who I think spoke yesterday morning, she's the director of our systems department, space systems department, where all our avionics and software work is done. And somebody decided, I guess it was 7 or 8 years ago, that they thought that'd be a good idea for a propulsion hardware guy to go down and manage a avionics and software group. And boy, that was a eye-opening experience, and one that I actually have really I loved at the time and have continued to lean on from an experience standpoint. And so I just want to let this community know that I really do appreciate what this group does, and got to better appreciate it over the last several years that I worked closely with our flight software development team. Let me just comment a little bit about what I think makes software engineers some of the best that we have. And what I observed, kind of coming from a hardware background, was that the real unique thing that our greatest software engineers had to do is they had to take a bunch of other what I might call disjointed and chaotic system and discipline people, and their ideas and thoughts about what they needed functionality wise, and they actually the software folks actually have to force them into a logical thinking, which is a great characteristic to have, and actually writing down what you wanted that functionality to be in ways that could actually be implemented in software. And so I came to appreciate that some of what I still call today our absolutely best systems engineers, I believe, systems integrators, system designers, we use that talk a lot, actually come from our software community. And I think that's a real, it's a what's my word here? I'm looking. It's just a real a great thing for this community to produce folks that are thinking at that level and really do see the systems in so many ways more than our hardware people do. And so I just wanted to kind of throw that out there. Another thing I observed as I was working very closely with the software community was that I also envied this bunch, because I don't know if many of y'all have experienced this, but coming from a hardware background, most every manager, and especially top managers in the programs that I've been associated with, almost know nothing about software. Does anybody want to say why that might be a blessing? Well, come from a hardware program, everybody and their brother thinks they know something about what you're doing, and they're always more than happy to comment and give you ideas or direct you to do other things that you as a hardware guy may not necessarily want to do. And what I observed in the software community, again, that there was freedom and some level of trust that group knew what they were doing. And they got beat on, don't get me wrong, but it was mostly for schedule, when you're going to deliver, and have your requirements settled down, and how's the testing going. But getting down into the nitnoids, as I've seen kind of from managers in some of the other areas, has not been the case. And so you can count it a blessing as a flight software and software folks, I think, and I found that to be quite interesting, that the trust that the programs have to have in the software community, because many of them don't understand it, is good. And of course that brings some job security too. I hope you guys know that. And let's see, what else was I going to mention about that? Oh yeah, going back to this idea that I think our software community can produce some of the best system thinkers, system designers, integrators, and those kinds of things. I would just encourage this group to continue to, do the great flight software work that you do, but also I think we don't, as a community, a flight software community, we don't push some of our colleagues into some of these other management roles and systems integration roles that I personally would like to see. I think our programs could benefit from that. And I know you guys a lot of times, love doing what you're doing, and it's hard to maybe get you to want to move into some of the other areas. But I would like to encourage you, but just because I know the backgrounds and the kind of thinking that has to be done to do the work that you do, that the programs and projects could very much benefit from managers and leaders that have come from this background. So it's just something I wanted you guys to think about when an opportunity to mention that to you. I've also often commented, and I know our software folks have heard me say this many times before. Of course, y'all know we're doing the flight software in-house for the Space Launch System. And when I want to know something about the vehicle, right, the Space Launch Vehicle, I go to the software folks, because there's nobody that knows that total integrated vehicle more than the software folks. And I often tell our higher up, center director and other folks, they talk about integration and systems integration, and I'll say, hey, the folks that are doing the systems integration on the Space Launch Vehicle are the software team. And that's because they've got to understand every aspect of all the functions and how they come together. And they're the folks that are doing the testing. They're the ones that have been seeing actually this vehicle fly and all the data that's been simulated for months and months now, right? And so they're the ones that actually know the vehicle. And again, it's a testament to this group in all the work that you guys do and kind of the knowledge that you bring to the table in support of all the programs that you're supporting. And I just wanted to let you guys know, again, going back to my original comment, that I love flight and software development in general. So anyway, enough of that, but I did want to express that while I was here. I've got a few charts here where I just want to show some of the things that kind of what we're looking at Marshall from a software engineering standpoint. I know Tia Ferguson has talked about it, and probably others, got some of this on the tour, but hopefully it won't be too repetitive. But obviously, let's go ahead to the next chart. I'm going to talk about enabling technologies. Many of these, or all of them, probably won't come as a surprise to you guys, but this is kind of how we look at the things we're focused on as moving into the future in flight software arena. Of course, from a space side of the business, the further away we get from the planet and the less or the least costly operations, we recognize that we want to be moving into more autonomy and including navigation and decision making that has traditionally been done with human beings and software and some combination of that interface. But we really are, starting to put our mind and thinking our mind on how do we write software, test software for autonomy. Of course, our automobile industry and other autonomy folks are thinking about some of the similar problems that we know we'll face. But that's kind of things we're looking at. And, of course, being at Marshall, being a science center and also a human spaceflight center, we kind of sit at this precipice where we will be attempting to integrate more of our scientific missions and payloads in with our human systems and our exploration systems going forward, and we know flight software is going to be playing a big role in that. So we're constantly trying to think about how do we, again, a lot of autonomy of how we integrate these complex missions. Of course, if you're in our business today, project schedules and budgets are one of the things that drive us. They always want things quicker and faster. They want to be able to change on the fly. They want to be able to, come in one day and decide to do something different and it not affect the schedule or impact anything, which we've all found to be quite impossible. But those are the challenges that we have. And, of course, software is a big part of that. And our thinking, as I'm sure is this whole community, this idea of being able to reuse software, making it more modular, being able to combine it with leverage previous software developments and put it into the future, we think is certainly going to have to be used more and more. We are starting to look, I think I've got another chart on this, about how we, and this is, we're starting to really get into this as we're doing more and more of our testing there in the SEAL laboratory that you guys saw yesterday, just the reams and reams and volumes of data that's coming out of our test campaigns, and we just don't have enough people to actually look at those things. And so we do see where machine learning, AI technologies, we've got some activities even now that are starting to look at some of that, are going to play a role. And then I think all of us as a community are having to think about software on higher performing hardware systems and how do we write software differently? How do we take advantages of these higher performing hardware systems and deliver on our mission needs? Let's go to the next chart. All right, so I think these next 2 or 3 charts just kind of give a little more detail of the capabilities that we've been trying to work on. I'm going to talk about our human rating software experiences. We've got some experiences in autonomous operations and capability we've developed. Of course, I think y'all have already been talking a good bit about core flight software. We're very much trying to get more involved in that. I know some of y'all probably have a lot more experience than Marshall does, but that's one area we're obviously looking for more partnerships with folks to continue development work and applications work in core flight software. And then, of course, we have put a lot of investment. I hope all of y'all that went out to our Hardware in the Loop system integration lab yesterday saw that we are big time engaged now in hardware in the loop and in simulation activities for large complex systems, and that's another area where we would definitely like to be engaged in partnerships. Let's go to the next chart. So let me talk a little bit about our human rated. Next chart, please. Maybe I got to control this. Let's see. Maybe they left. There we go. Yeah, so Space Launch System. We're doing the flight computer software. I think you guys saw this yesterday on the tour. There's three flight computers, and we are doing a voting architecture across all three of those flight computers. That's been quite complex and interesting, but I think we've got the kinks and bugs worked out of that. We're doing that on the Wind River VxWorks platform. The real-time platform has worked very well for the folks. And then, of course, the iLoad software is one of those things that day of launch upload that'll have to be done for the flight software. We think we have the kinks worked out of that. It's been quite interesting getting through all of that activity. And of course, at Marshall, being and you're here in the Rocket City, rockets are our thing and spacecraft. But I tell you, some of the most interesting software work that we've done and that I got to enjoy when I was in the Space Launch System is some of the stuff that we're doing for the International Space Station when it comes to payloads or those vehicle systems. You guys saw some of the work we were doing in our environmental control and life support, our UPA, the old urine processor. Any of y'all get to taste any of that recycled water? They usually have some water bottles down there. Didn't? Okay, yeah. So anyway, good stuff. And the 4-bed carbon dioxide scrubber system. Did they happen to show y'all that system? Anyway, that's some new technology that working. It's a test bed that we're trying to get up to the station right now. Hopefully we'll be flying next year up to the space station. But the control software associated with that system is fairly complex and very interesting. And then one of my favorites is our material science research rack that we have on station. And there's just a lot of control that has to go on and a lot of human interface to the hardware. And so that software can get quite complex and very interesting work. So I actually enjoy all the science work that we do. Modeling and simulation. Let me just comment on this. I know our software team, and the program guys, I commented on the program guys, they kind of let the software folks alone a lot of times other than, beating them over the head about schedule. But one of the things I've observed in our development here, the flight software is complicated in and of itself, but the Artemis and Maestro suite that actually operates the real-time simulation lab is a monster of a software development. I hope y'all that have been involved in simulation environments and in a real-time simulation environment that has to simulate real-time all the environments of the launch vehicle and that'll be flying through. I have been extremely impressed with the complex software development job that's had to go on just to provide the simulation environment for the SLS software to be tested on. And I'm very proud of the folks that have done this work. And Tia actually told me she had forgot to mention this. Hopefully maybe Ashley and some of the other folks that will be talking later today can give you guys more detail. But one of the things we had talked about 2 or 3 years ago was, boy, we sure have invested a lot in this real-time framework for simulation. It sure would be nice to be able to scale that down and use it on our smaller activities. Spacecraft, do a lot of CubeSat work, those kinds of things. Smaller spacecraft than the launch vehicle. And so we worked with some folks and have basically scaled our Artemis Maestro kind of suite down to where we can actually use that on other test beds. I think I may have another chart on that. And so that was a real big accomplishment, and hopefully some of y'all will talk a little bit more about that detail. But that's certainly an area where we'd be interested in partnering taking this capability that we use on SLS and putting it in a simulation environment for other programs that you guys may be interested in. All right, let's go to the next chart. So some of the work we've done in autonomous operations, of course, got Space Launch System. We do pick up a automated launch sequence at basically launch T0 minus 30 seconds on our SLS software, and it runs through all the way through our interim cryo propulsion stage separation. So the flight software is in control during that period of time, doing off-nominal and vehicle health management. Of course, got a lot of algorithms looking at various aspects of vehicle health management. And then a little program that some of y'all may have heard of, demonstration of autonomous rendezvous technology back in the 2000s, a program called DART. Our software group was heavily involved in this thing called the Advanced Video Guidance Sensor, and autonomy that was required for that sensor, which was a big part of the DART mission as the spacecraft was chasing down the target spacecraft. By the way, that mission was did not turn out exactly like it planned. We were supposed to go out and actually rendezvous with the target satellite, do some maneuvers in and around it, and but we actually did end up actually touching the satellite, which was not originally planned. So our sensor actually worked. We had some other problems going on, but this was some real good autonomy work. And then some of the work we're still involved with and have been as a part of the Advanced Exploration Systems program. Actually, some of this work had been being done with JSC and Marshall is on this autonomous fluid transfer system. We actually set up a lab where we had these liquid tanks that were simulating, potential systems on space station, and we were doing autonomous control, transferring fluid from one tank to another, and trying to do all of that work with software and autonomy, and a good bit of that work is still being worked on. We're still funding some of that with some of our technical excellence, IRAD kind of activity where we're looking at that. And then another area, as I mentioned earlier, that we're trying to look into is with machine learning. We think we have a real opportunity with the SLS data that we're getting off our testing to apply some of the AI machine learning kind of activity to help us analyze some of that data. Next chart, please. Okay, so I mentioned that I know some of you guys have probably a lot more experience than we do with core flight software, but this is something I know I was pushing when I was down in the lab that I really felt like we as a Marshall software group needed to get on board with the core flight software, and I think we now have a lot of believers in that and are making strides. The Lunar Catalyst program, which I think Tia probably talked about yesterday, this is where we were helping several of our commercial lander partners working on robotic landers. And so that was really our big first hooray into core flight software. And I think we got a lot of our folks interested in using that software package. So very nice. And then Marshall, I don't know how many of you guys know, but we're partnering with JPL. Currently in the role that Marshall has is on the Mars ascent vehicle. Developing that vehicle will take the Mars samples off the surface back and rendezvous with the spacecraft that'll bring them back to Earth. And we are developing prototype flight software on core flight software for that mission, for the actual Mars ascent vehicle, which is basically a rocket, small rocket that'll come off the surface of Mars, doing that in core flight software. And we had been working a smaller avionics test bed for an iodine CubeSat satellite that we'd been working in-house, and we've been porting some of that software that we had done earlier over to the core flight software. And as I mentioned, we are still trying to use some of our funds and opportunity to train our folks in core flight software. We see a real real opportunity to expand here as well. Next chart. Okay, so hardware in the loop capability, we kind of talked about this. Many of y'all saw this yesterday, and I'm sure Paul gave you guys a good tour. Again, I'm most impressed with our simulation system, our ability to interject hardware. It's been incredible. I don't know how much Paul has actually was able to relay actually how much we've learned and problems and issues that we've corrected by being able to have this environment of simulation. You know, when you plan out a program like this, even the hardware in the loop laboratory, you know, always plan that your hardware, your actual flight computers and RENUs and all your other boxes, flight hardware boxes, are going to show up at a certain period of time. Well, guess what? That never happens, right? There's always issues. And so, no kidding, in all of our setups, we've had hardware trickle in, but because of our simulation framework, we've been able to continue to just add a piece of hardware as it was able to get delivered and continue to basically fly the vehicle, test the vehicle, and just keep adding hardware as it showed up. And so that's been a real blessing and has really driven out a lot of our issues. It's something we're very proud of. And as I mentioned, we've been able to scale this down and can make it available for smaller projects as well. Let's go to the next chart. Yeah, so okay, I mentioned that configurable, scalable framework. It's got reusable test control modules and displays as a part of the setup. We've proven most all the I/O interfaces from the 1553, GigE, of course your standard analog and discretes. Selected the real-time computing platform. I mentioned the VxWorks there, and then established architecture for test data, archival and analysis. Again, when you've got a lot of the work this group has had to do in recording all this test data, right? Okay, well, where are you going to put it, and then how do you get it distributed out to all of those different groups? Our GNC group being one of the big groups that are using their simulation data for their verification work. That's been quite the challenge for the group is how do we move that test data, large quantities of it, and get it to the right people at the right time where they can do their verification work. So big stuff going on there. Let's see. Let me go to the next chart, I think. Oh, yeah, so this basically is I was thinking that was the last kind of chart I wanted to talk about. I had some final thoughts I wanted to leave with you. Yeah, so I hope what you're starting to get a sense of through this whole conference and the tours yesterday, and hopefully what more of the details you'll hear in presentations from some of our software folks this afternoon is that Marshall Space Flight Center is in the software development business, both flight and payload systems, and we're here to stay. And we are wanting to continue our partnerships and seek new partnerships. We have a lot of partnerships with the industry already, but we would really like to grow our software capability. Continue to work with folks like you guys in all of our programs and projects, and then start to continue to think about how we some of the technologies and the vision of where we've got to go as a community, continuing to work together. I believe you will find a very competent flight software and hardware integration folks, simulation folks on the Marshall team. And more than anything, I think you'll find folks that are easy to work with. That's not always easy to find, but again, most of these folks are in a Southern hospitality environment, and we love friendships and relationships, and we believe that's what it takes to make good development teams, and nowhere is that as important as in software. So we appreciate what all you folks are doing and the work, and with that, if there's any questions for me, I will be glad to talk about that. I saw some of the interesting comments that Eric Berger made yesterday about the space program, and Lynn was telling me he thought NASA was the North Alabama Space Agency. That he
Yeah, I
made
never
that.
heard that one.
That may not be what you want to be known as, but anyway.
Questions? Nope, I see. Let me get this young lady here.
Thank you. You talked about how your hardware people are often don't have a good understanding of software. What do you do to educate people who don't have software backgrounds?
Yeah, that's a great question. I think you kind of got to do what the experience I had. You have to be intentional and deliberate about getting those people together, and kind of forcing the hardware people to learn the what the software folks do, and vice versa, right? And I think a lot of the times we just kind of let that try to happen. I think we could be more deliberate and intentional about having training sessions, opportunities to. I'm talking about as a team, right? That when you got a hardware and software team working together, a lot of times we don't. A lot of times, when we lay our schedules out, we just put our milestones on our schedules of product delivery, right? We don't ever think about the schedule that needs to be there regarding team integration, team dynamics, team understanding of each other's roles and what they're doing. And I think we could be more deliberate in planning out those opportunities for the team that's working on Project X, Y, or Z to actually learn more about each other's discipline. And so that's kind of what I would say to that. Others may have comments they'd like to make on that too. Ashley.
We do it primarily through our teaming activities. We take advantage of, setting up the teams and structuring the teams so that they collaborate amongst other disciplines. It's a little bit of a feedback there, sorry. So I probably can speak loud enough. But one of the things we do at the team level is we pair program with younger engineers or engineers who maybe don't have the discipline knowledge within that domain. So we partner them up with somebody with a lot of experience in that area, and so they're able to more organically grow in that area. And then we do, especially on the Artemis side, because Artemis is so complex, we do have training sessions. We call it Cooking with Artemis and Maestro classes that we give periodically to testers, hardware engineers who don't understand the simulation. It gives them some insight into how the simulation is structured and how it's run, how to execute tests, those kind of things. So he's 100% correct. We could probably do some more things more deliberately to educate people who don't have the discipline of software engineering, but schedule dictates and you do what you can do within those constraints.
And I'll add to that too. So for software, we are doing an overview with teams that are unfamiliar with our software system. So we have kind of a roadshow to come and provide somewhat of an overview and partially deep dive into the architecture of the system to help the hardware team understand the functionality of the whole system.
Hi, Larry. I'm Charlie Hone from Northrop Grumman. This is my partner in crime here, Robert Bruckert. We are actually involved more in manned aircraft, and we are probably have different requirements than what is provided by CFS, but nevertheless, Robert and I would like to kind of connect with the community, keep an eye on it, and see where that could possibly lead. How would you recommend that we start?
Yeah, I mean, I think Scott and Lynn here would be some of the right points of contact to get in touch with. I know our Goddard folks have a lot of, being kind of the originators of core flight software. But these folks know how to get you in touch with those folks. Some of the Goddard people may be here today also.
Thanks, Larry.
Yeah, you're welcome.
Any questions?
I was curious about model-based systems engineering and whether or not that initiative at Marshall has involves the software side, or if it's pretty much on the systems engineering side. Could you speak to whether or not that's currently being implemented within the SLS program, or if it's just in development for future projects?
Let me see. Some of my folks can comment on this, but from my knothole, model-based systems engineering as a whole is not being used on SLS. We are doing the systems engineering. However, we do have several what I might call piloting activities for model-based systems engineering, some of which is even on SLS. But I would comment on this. You know, a lot of the model-based systems engineering initial activities on the what I just call the requirement side is really heavily based in SysML and the ability to use SysML and do that modeling in SysML. And from my observations, our software systems people are really some of the best modelers that we have. And that's one of the things I've been looking at as an engineering director is we try to advance our model-based systems engineer for any program. And by the way, we're looking at, we're doing more and more of that on the Mars ascent vehicle that I mentioned. But I really think, from my knothole, the folks that are our models, our system models that we have for software are really leading the way in what I think of as model-based systems engineering capability. And the group that has been doing that modeling on SLS, I think is some of the best in the business. And I personally would like to have some of those folks come help with our larger model-based systems engineering effort. I think that's where our real expertise really is, because of the job they've had to do in the system modeling, software systems modeling, and the design of that system. Any of you guys that are more familiar with our software system modeling, having comments? Ashley? Yeah, go ahead. Oh, you did?
You had such command in the room.
Oh, yeah.
I should wear my glasses. Larry's right. We do model-based systems engineering activities in pockets, little pilots around the center. In reality, model-based systems engineering is something near and dear to my heart that I've been involved in for years. It's a cultural shift, right? You got to really change a culture. And so we're doing that as organically as we can, sort of at the grassroots level. We've got groups like M&FM, our Mission and Fault Management group, that does a lot of SysML modeling to model their algorithms. We have groups that are working UML type diagrams using Magic Draw to model the software. We're trying to figure out as a organization how we grow that into true models-based systems engineering. So it's growing slowly, but you know, it's a cultural shift as well. So
I meant to our Northrop friends here made me think of this excerpt from this article I meant to actually share when we were talking about the future and the complexity around our systems and software. I don't know, this article came out, this was on the Boeing 737 MAX 8. I know all of us have been following that in the news, but I had found a article interesting here a few weeks ago about that I wanted to share with this community, and I know you know it, but it says, "We did not see that anybody intentionally did anything wrong," he said. This talking about the FAA. He said the FAA certification process is in need of significant updates to reflect, among other things, the complex interrelated systems in airplanes today. Here was the quote I wanted to share. "The good news is there's more automation. The bad news is there's more automation, right? And I really, as a software community, right? I mean, I know you guys see and experience that other day, and you think about how do you test all of that and all the different scenarios and the complexity around that. And that is, it's the good news and the bad news. But that's really our challenge as a community. Is I don't think we can continue to approach our work like we have in the past as things get more complex and we try to do more things with software and hardware and health management and all of those things, real-time stuff. We've got to think more innovatively. I don't have the answers, but I suspect folks in this room collaborating can get to those. Any other questions?
Other questions?
All right. I hope y'all have a great rest of your week. You'll be hearing, I'm sure, other interesting speakers the rest of the week. I'd like to invite you back to Marshall anytime. Hopefully some of y'all that didn't get to come out and do the tours can come back sometime. We'd be glad to host you. And again, we're looking for partners, collaborators on pushing this software discipline forward in the future. Appreciate your time. Thank you.
Thank you, Larry. So we weren't very successful in having a raffle a few minutes ago. So we had like 20 tickets and finally we got a winner. So we're going to do a few raffles. We have the Bluetooth speakers that MathWorks provided. So we have like a lot of these. So we're gonna do like 3 of these like right now, right? Okay, so let's make that happen. Ticket number 121. $142. I see one hand in the way back. Well, Jim.
121 and 142.
Yeah, I'll put it aside. Nope, never mind. He's one of the committee members, committee folks. 13. $139. 82. Huh? Nope, you can win more than once, so you can give it to a friend. That's why you got that bag there. All right, let's do another one. 84. You pass that down. What's that? 84. $131. All right, he wants it. That's Brandon back in the back. 58. Nope. 48. All right. All right. Yep, I got it up here. Okay, so if we can, we'll go ahead and, are you guys ready?
Yeah, we're ready. I thought you were going to call 117.
Well, we could. If we keep at the rate we're going, we would get there. All right, our next presenter is Ashley Lee. Are you going up also, Jared? Or?
We're going to all tag team this.
Okay.
All right.
That one has a drop out.
Can you hear me?
It's definitely much better.
Probably could hear me without this. So this may be a little repetitive because we've been talking about Artemis and Maestro here quite a bit. And if you attended the the tours in the lab yesterday, you got a little sprinkling about Artemis and Maestro. How many of you attended the tour yesterday? What'd you think? It's pretty cool, isn't it? It's pretty awesome. A lot of work has gone into building that lab in particular. And you probably didn't get around and see our Sprite lab, which is our Small Projects Rapid Integration Test Environment lab, which is where we do a lot of the small sat hardware in the loop testing. And you probably didn't get around and see the software development facilities, did you? Where the flight software is being developed. Okay, great. So there's just, you saw that large lab. I think I counted 26 different labs, configurations that we support from an Artemis and Maestro perspective. That includes the 5 software development facility lines, the CITIF-Q qualification line, CITIF development line, the SIL, the booster hardware in the loop labs, the TVC lab, and that includes all the emulator development and test lines that we deliver as well. And in addition to that, we have test development lines where we qualify and verify the Artemis software and the Maestro software. And we have development labs, multiple development labs that are in various configuration states to match the intended production environment. So it's a challenge, a version control, configuration control challenge. But I'll talk a little bit about how we've met that. So next slide, please. Or am I the advancer? You got it, Jim? Thanks. So give a little context here. It looks like my videos I probably forgot to attach those when I sent the presentation, so that's my fault. Little context here. This is really leading to why we developed Artemis and Maestro, right? So vehicle failures are expensive, right? I believe the Titan 4 A20 back in 1990, estimated cost of that explosion was over $1 billion. They can be very dangerous. In this case, the U.S. Navy submarine launched a Trident missile, and it sort of came back like a boomerang. We didn't want that. And then, of course, the human element. We have lost lives on the vehicles, and that is always first and foremost in our mind as we develop any spacecraft vehicles or anything that's in support of testing those vehicles. Next slide. And somebody turn the AC on because it is freezing up here. So, back then, technology during the Apollo era was, it was lacking a little bit. We didn't have as much power in our PCs. But in 1971, Intel introduced the first microprocessor, which was the Intel 4004. And so that made some strides. We were able to start making strides in our technology improvement. But back then as well, there were no vehicle simulations, just test flights. Okay, build it, test it, explode. Don't do that again. Got to change something, right? Next slide. But now we've got multi-threaded operating systems running on high-frequency multi-core microprocessor hardware. We've got vehicle simulations that have become possible now with better risk profiles for human crews and test hardware, and it's less expensive than doing test flights over and over and over. So we can run, as Tia said, 1 million different tests before we ever put the hardware on the vehicle and launch it. So we can have a high confidence that the vehicle and the flight software is going to perform as intended, both in nominal and as many off-nominal situations as we can come up with. You can't test them all because you can't always think of them all, but as many as we can possibly think of. Next slide. Bam! In comes Artemis, right? So Artemis, and by the way, the program stole our name, just to let you know that. We had the name first. But we like to say we say it loud because we're in all caps. So you see it in all caps, you know you're talking about Artemis, the simulation. Artemis is, it's an acronym. It stands for the Advanced, probably would be more aptly named Adaptable, but it's Advanced Real-Time Environment for Modeling, Integration, and Simulation. It provides the real-time hardware-in-the-loop environment for hosting the system and the simulations for aerospace vehicles, robotic systems, small spacecrafts, and it stimulates hardware under test. So it is capable of stimulating the components, the sensors, the effectors, even the motion systems. We do a 6 degree of freedom lab here where we stimulate the legs and we move the floor. It's reconfigurable for vehicle design. Larry mentioned that, we've taken Artemis, which you've seen in the lab, spread out across those 6 towers on each half ring, 12 to 13 comp nodes each. We've distributed Artemis executables across all of those nodes so that we can achieve real time. That's a pretty large simulation environment, pretty intensive. But we've taken Artemis, the framework of Artemis, and we have scaled it down and put it on a small portable hardware-in-the-loop test bed. It's like a suitcase that you could plug your own individual I/O cards in and out of and connect it to your small satellite or your vehicle, your small spacecraft, and run a full-up Artemis simulation. So we've proven that the framework is scalable. Next slide. So why Artemis? And you're going to hear my sales pitch here, but it supports multiple levels of model fidelity. One of the major things we did for the program is, as Larry mentioned, hardware is not always on time. It's delivered sometimes late, sometimes it gets delivered and has to be redelivered because there are issues. Well, by being able to support multiple levels of model fidelity, we've enabled the program to be able to continue to test continuously while that hardware was being designed and matured and readied for integration into the lab. So we could take early low fidelity representations of those avionics components and we can plug them into the lab and do some testing, and then as the hardware design matures, we upgrade the fidelity of the model and we continue to iterate until we're to the stage that we're at now, which is the lab has been certified for phase 1 testing. It also supports vehicle dynamics, flex body, rigid body dynamics, selectable winds, atmosphere, TVC nozzles, etc. And it supports non-real-time, all-digital configurations. So if you don't have any hardware and you want to run an all-digital configuration, we've pretty much modeled the entire vehicle. We've even ported in the flight software so that you don't need flight computers and you can run an all-digital simulation. And of course, it supports real-time distributed configuration. That's the main, power of Artemis. It supports multiple development and test labs, as I've mentioned, and it's portable between Linux distributions. I think right now we're on Red Hot Concurrent 6.5. Is that right, Pat? Dr. Pat Toby, he's the chief architect of Artemis, so he is probably the most versed in all the particulars of the simulation. Artemis operates in a hardware-in-the-loop environment where the user can select different models, component models, subsystem models that they want to actually run a test with because they don't have hardware, or perhaps they want to inject a fault because we don't fault the hardware, we fault the models. And so they're able to manually configure how the test is going to be run, what's real, what's not real, whether it's real or simulated buses, etc., and different fault scenarios. The simulation interacts with the lab configuration and control software, as well as with the facility monitoring system. So it's integrated completely into the lab. And it utilizes modern computing technology to achieve real-time performance of high-fidelity models. The Red Hawk Concurrent RTOS system, multi-threading, and we use the C language. It is written in C, which we've all, learned a little bit about. It's not type safe, so you have to be very diligent in your memory allocation and your type declarations. Next slide, please. So what were the drivers for requirement, or the requirement drivers for Artemis? Well, we needed to be able to model the vehicle with high fidelity in real time. That means low to high fidelity models of all the avionics components of the vehicle so that we can run an all digital simulation if we need to. Low to high fidelity models of all subsystems that affect the vehicle or interact with the avionics. And the low to high fidelity models of the environmental effects, the atmospheric conditions, the flex, slosh dynamics, model dynamic effects as well, which I just mentioned. We also have to be able to model all phases of the missions, from pre-launch, 36 hours before launch, all the way up through orbit insertion. So we can run in real time the simulation all the way from 36 hours prior to launch, let all the ground systems do their iterative processes, all the way up until we hit T0 and then up through launch, through orbit insertion, which is at about 600 seconds, I believe. Support of multiple labs and configurations. This one has been the most amazing part to me, is that the myriad of lab configurations that we support in various states of hardware integrated into the lab. Some labs have no hardware, some labs have maybe a flight computer, some labs have flight computers and CTCs, some labs have flight computers, CTCs, RENU, and it's just, it's a broad spectrum of configurations that we have to be able to support. All right, and that in turn, runs into the scenarios for each labs. We have to be able to support user-defined scenarios for their test because every customer is different. We support Kennedy Space Center, the electrical ground system folks. We support multipurpose crew vehicle, the Orion folks. We support SLS. We support core stage. And all of them have different goals for their test. And we have the software, the simulation has to be configurable and has to be able to support various scenarios that are defined by the user. Next slide. We have to be able to execute in multiple modes of operations. That's non-real-time, real-time modes of operations. All simulated buses or all simulated hardware. Interact with the lab configuration and control software, as I said before. And we have the fault insertion capabilities. We have configuration selection and the generation of scenarios. We have data recording and archiving, where each hardware bus has to be recorded and archived, and it must be archived in the HOSC, which is the SLS's data storage location, official data storage location. So we have to push data from 4205, where the lab is, over to another building so that it can be retrieved later for analysis. And we have to make sure metadata is provided for all the recorded data as well. Next slide. So the design of Artemis, and I'm not going to get way into the weeds because we only have 25 minutes here, but I have some backup slides as well. And of course, if you want to know more, you can always contact myself or Jared or Dr. Toby. But at a high level, the Artemis simulation consists of a simulation executive. It has separate executables for each model. It allows plug-in operation for switching the model with the line replaceable units. The models have to be distributed so that we can achieve real time, so therefore you have all the comp nodes that are around the frame of the systems integration lab. And all models have to be hosted on a simulation node that's located in the correct physical location so that we can have the cables, the correct length of cables, running from box to box that'll be on the vehicle so that we can test the entire system and the attenuation of the signals through those cables, the latency, everything. We test it all. Single copy of source code. So that's how we achieve being able to distribute all these different lab configurations. It would be a nightmare to try to manage multiple branches of source code based on the configuration that you're in. It becomes a version control hell, if you'd like to. We did it for a little while, and it got a little out of control, and we had to pull everything into a single source code trunk. So otherwise, we were going to go crazy. But that's how we do it. We have a single source code trunk. The simulation's highly configurable, so we deploy that single branch of source code everywhere. And then based on your lab configuration, you tweak a few node mapping files, configuration files, and you're ready to go in your lab with the same software that's in another lab that's completely configured differently. All models utilize the same libraries to allow for ease of incorporation and maintenance. That's your intermodal communication, hardware communication, I/O configuration files, your input file parsing, data recording, utility functions, all of those are shared. The vehicle configuration logic and dynamics engines are generic in order to support changes in the vehicle architecture based on your design analysis cycles or your FRAC cycles. Shared memory region used to transfer data between models. We have a blackboard structure that is defined to include all the data that's shared between the models in the simulation. Each model owns its own particular contiguous section of Blackboard. And we use InfiniBand as our backbone in the Artemis simulation to move data between the models in the simulation. And models update the Blackboard section at the end of each time step. So it's a 2.5 millisecond time step within Artemis, and all the models read, execute, and write within that time step. We have a fault insertion engine that can override real-time inputs to the models. We do that via peek and poke from Maestro, which Jared will talk a little bit more about. And we have separate fault insertion executables that can be written that can take advantage of the command timeline and execute faults at certain times within the simulation. Next slide. So I started a little bit on the framework. The framework, Artemis is composed of two major parts. You have the framework, and then you have the plant model, which is the vehicle. So the framework is separate. It's version controlled separate. That way you can change the plant model anytime you want. It can be a large launch vehicle. It could be a small satellite. It could be a robotic system. The framework consists of the simulation executive, which essentially provides the main for each model. It provides access for models to connect to sync, connect to the I/O layer, so it's really the wrapper for the simulation. The timing, synchronization and timing, it manages the scheduling, the global timing source. We use RSIM cards. I believe, Pat, do we still have iRig-Bs in the sim, some environments? We keep all the executables on each node in lockstep, and it manages the InfiniBand and Blackboard shared memory on each machine. And we have the models. The models are consist of the core sim models, which are our dynamic environments, our vehicle configurations, our subsystem models, which includes the model effectors and sensors, the interfaces between core sim and the component models. And we have the component models, which are the avionics. And then we have an I/O layer, input-output layer. And this layer is responsible for all the communication between the models, between the simulation and the hardware. It has shared memory as well, and it can model the 422 cards, the 1553s, gigabit Ethernet, D to A to D. It models and provides I/O capabilities via all those drivers. And data recording. We have data recorders in most of our labs, not all of our labs, and sometimes that can be challenging when you're trying to debug if there's not a data recorder there. But it records all the hardware bus data, sends data to a remote archive, and provides global, local, and metadata definitions so that you can decom that data and use it for analytical purposes. And Artemis also consists of hardware. So the comp nodes that you saw in the lab, the SIL, were Artemis hardware. The I/O cards, all the I/O cards that we support are part of the Artemis simulation. And the cables and the racks that we provide when we give emulators out. So Artemis is also considered hardware as much as it is software. Next slide. So just a quick overview of the simulation executive. It's a set of libraries that are linked into each executable that provides a easy-to-use interface to Sync and to Maestro, our test conductor interface. It provides access to a common set of functions, utility functions. It does require that each model populate a set of wrapper functions in lieu of a main function, and each wrapper corresponds to a particular simulation phase. And I'll talk about the simulation phases here in just a second. And the executive cycles through the simulation phases as commanded by Sync, as many multipasses as necessary. And during the run, the executive overhead is, we try to keep that to a minimum so that we don't blow our frames. And it provides the ability to run models at two different frame rates. 2.5 milliseconds is our frame rate for Artemis, but some models run even faster, up to 100 microseconds. Next slide. So the phases, the simulation phases. You have startup, which is where we set up the multi-threading, we do any input file processing, and we register the models with Sync. The initialization, as commanded by Sync, allows for models to initialize based on output of other models, and this can happen on many passes as necessary. It handles Blackboard data transfer after each pass, and the data recorder setup occurs during the last pass. And then it moves into a scheduled phase where the reads and writes to the I/O layer occur, nominal model function calls occur, the Blackboard data transfer occurs after each pass here, and models have an option of buffering Blackboard data for read-write protection when using the minor frames or the minor frames. And then shutdown, where we close out the I/O layer and the local data recorder connections. Next slide. And I know I'm going fast, but I got to give Jared time to talk as well about Maestro, so I apologize. Quick timing and sync overview. Timing, sync or synchronization component, we call it sync, controls timing and scheduling for the frames. For each Artemis executable, they can run at different frame rates that are a multiple of the sync minor frame rate. And it maintains hard real-time operation using a timing card such as RSIM or iRig-B, but we can also run non-real-time with our sync as well. And it creates and controls access to the shared reflective memory region of Artemis, known as the Blackboard. And it receives and responds to commands from Maestro for both master and slave syncs, and I'll talk about that here in just a second, the architecture. Next slide. So, master-slave architecture. One master sync process runs on the master node, and then each additional simulation node runs a slave sync process that's controlled by the master sync process. The master node controls real-time synchronization via the reflective memory, where it receives timer interrupts from the timing card. And the sync is responsible for data coherence, making sure that the data input at the beginning of the SIM thread's start cycle and that it outputs at the end of the cycle prior to the SIM thread's next start cycle. So very high level there, very high level. Next slide. Models. So we mentioned the component, subsystem, core SIM models. The component models, again, model the avionics components. The subsystem models are your sensors and effectors. And your core SIM models are your dynamics and environmental effects and reacting to forces and flow rates on the subsystem models. But we also have emulator models, and these model subsystems, components, and dynamics beyond the scope of the program. So these are our cross-program partners, where we're modeling ICPS, where we model multi-purpose crew vehicle at some level, low fidelity within Artemis, where there's not a delivered Orion MPCV emulator in a lab. In the SIL, you saw the blue and white box. That was a delivered emulator from Orion to us. But in other areas, like down at KSC, they do not have an MPCV emulator, so we have an in-house developed MPCV model that acts as an emulator for them. Next slide. So real quickly, elements of the core SIM, because this is really the meat of Artemis itself. You have the configuration manager, which manages the stage and mass configuration, calculates all the required inputs for the dynamics. You have the vehicle dynamics, which implements equations of motion, performs the numerical integrations, and calculates the state vectors. And then you have the environment, which computes planet ephemeris, right? True of date, gravity, and then atmospheric properties as well. And it computes the environmental forces and torques, your aero, your gravity, parachutes, and you'd have to educate me on parachutes, Pat. It's a little bit beyond my understanding. Vehicle forces, computes forces from hold down posts and slosh. Next slide. The I/O layer is the other major component. We talked about the I/O layer briefly, where it provides a transparent, coherent, and consistent architecture for performing I/O from Artemis to the models to the hardware. It handles simulated device communication between the models via shared memory or ScramNet memory when we're talking to other laboratories, such as out at the ITL in Denver. And it transfers to real or simulated devices. The transfer of data has to be transparent to the models. And it handles the following real devices, such as 1553, 422, discretes, analog, gigabit Ethernet. Here, and you can see I had a cut and paste error there because that's the Ares 1 architecture, but it also supports, Artemis has been developed since Ares 1, so it's been around for a while. And it handles other real devices needed by the simulation system, such as your, I think that's your generic purpose interface bus, is that right, GPIB? general purpose interface bus. There you go. And then your ScramNet GT, which is sort of a next generation version of ScramNet, and your iRig. Next slide. And the data recorder. The data recorder, again, supports generic data recording of multiple types of interfaces, all those interfaces we just talked about. It's configurable via XML, which is really nice because different labs have different I/O cards. Data is recorded in its raw format. Each packet messages is recorded with a timestamp. We have a requirement to be within 200 microseconds. So each interface is recorded in a separate file, and it interfaces with the Maestro daemon and provides periodic archiving capability for analysis during long tests. Next slide. I think this hardware would be the next one. Yep, not working. All right. And so just a real quick overview of the hardware. You saw these racks in the sill. Again, our simulation is built on the concurrent Red Hawk real-time operating system. The boxes are concurrent boxes. We've got all the I/O cards that we talked about. And the sill, as you heard Paul mention in the lab, has flight-like cables. That means they are the same as what will fly on the vehicle. Length, number of pins, everything. And all simulated components are positioned in the computer racks as near to the avionics location in the ring where they'll be on the vehicle. Okay. So I mentioned fault insertion. We have fault insertion capabilities within Artemis. There's really two types of faults. You can overwrite variables on the blackboard. That's the least expensive to implement, but it is limited to model-to-model interface variables, and it does not cover all your fault requirements. And then we have execute of an embedded fault scenario file within the simulation. That does require some expertise in writing those fault files because they are C files, and some VMV on those files to verify. It's initiated by tripping a fault flag on the blackboard, and there's some need to streamline a number of the embedded faults as we can within the simulation. There are two fault insertion mechanisms, as I mentioned, the peek and poke via Maestro, and then, of course, the separate fault insertion that I just talked about. So real quick, summary. Artemis, separate executables for each model. Single copy of source code for all its configurations. All models use the same libraries to allow for ease of incorporation and maintenance. The vehicle configuration logic and dynamics engines are generic in order to support different vehicle architectures. We have a shared memory region that we use to transfer data between the models, and fault insertion engine can override real-time inputs to the models via that shared memory. So next I'd like to bring up Jared Wilson. He's going to talk about Maestro, and then we'll take some questions.
I don't know. We doing okay on time? Okay. I think I can do it. Okay, so Maestro is another product we have that runs in the integration facilities. We're more on the lab framework side of things. It stands for Managed Automation Environment for Simulation, Test, and Real-Time Operations. We serve as the lab automation and configuration software for the integrated avionics test facilities, allows users to configure real and simulated and execute faults and events as part of the sim. We monitor the testing, and we can analyze the integrated tests like doing post-test analysis. Our requirement drivers is to configure the lab in a test environment to run tests in automated fashion, to interface with real-time vehicle simulation, display the test and facility data, to archive the test artifacts, and to perform the post-test quick look data analysis. We're kind of broken up into, we're orchestrated script-driven test control. We have a lot of Python scripts. We use we're heavy into XML file-based configuration. We have a middle architecture called a pub sub that sits in the middle that reads the shared memory coming out of the Artemis simulation for driving our displays, plots, tables, and things that the user would like to see at the display level. We distribute the metadata for the different bus types for allowing the displays. We have a flexibility in Maestro for plug and play for different node types. If somebody wants to bring in a new piece of hardware that wants to be tested, they can implement this new node type definition and integrate very easily into the facility. Maestro can run on Linux or Windows platforms. I kind of hit on a lot of this. We basically configure the lab. We start the whole simulation down to distributing the Artemis models to the different architecture in the facility. We configure the different node types to do their specific role as part of the simulation. We monitor Artemis. So if they have a critical or some kind of fatal error, we can bring down the facility in a acceptable fashion. We configure lab-specific equipment. So during the tour yesterday, they kind of hit on the data breakout boxes and the power breakout boxes. We configure those, what's real, what's simulated. We display the runtime test and facility data, and we've kind of hit on these. So this is kind of what the architecture looks like. We have a configuration manager that sits in the middle with all the configuration files and the software. We have a requirement that the software, we have to push down the software to our given nodes part of the test and guarantee that what's running down there is what's CM'd on our configuration manager. And we use rsync for that capability to do the checksumming to guarantee, because you don't want somebody messing with the software down on the nodes and not guaranteeing. So we had to meet that requirement. This is basically what the lab looks like from a software standpoint. This is really good to me. This is kind of the onion diagram of where we sit. We sit here in this lab outside this onion, and then you have Artemis, the models, then you have the IO layer that Ashley hit on, and then your hardware units under test that sit in the middle. So it's kind of an overview picture where Artemis Maestro sits, the models, and then down to the IO layer. This is a test case example. So we have you have the requirements coming out of SLS or the different programs. We map them to our test case scripts that the software testers and the verification tests that requirements that are needed. They're embedded into these Python scripts, and then they get executed part of Maestro. This is kind of what we hit on in the tour, and Ashley hit on it too. We have a test conductor. We have some middleware, a broker, a service, different services like a logging service, the pub sub service, and a test conductor node type service that communicates with the Artemis hardware and then the various emulators that we have in a given facility. Trying to go fast. Okay. Okay. This is a different type of configuration. If you went on the tour yesterday, you're kind of familiar with it. This shows if we have a actual MPCV emulator that was delivered from Orion program, or Artemis has an MPCV model given that it's simulated. So it shows this is the data breakout box we were talking about, and we can configure that over 422 data to the various hardware that is going to be used for the test. And then this shows the core stage ring that you saw there, the actual other real hardware in the facility. So this is my last slide here. So in a summary, Maestro, it orchestrates the test, it configures, starts and stops. It cleans up the facility for any models that may have gotten hung up during the test, or power that didn't go down correctly, or anything that needs resetting in the facility. We make sure to monitor that, so we can kick off a new test without any downtime. We configure like I said, most of the hardware and the if a user wants to do a fault case, we can configure that down to which node type that needs to execute that fault so it gets injected correctly at the right time during the simulation. We have lab-specific equipment, which I hit on earlier. That's if we have different emulators from different facilities that come into the lab, we have to be able to integrate with them. We have a, I don't know if, so I kind of have it here, hit on here, this SATCOM interface. We have this function dictionary type interface that's a NASA spec that where all the different centers have agreed upon it for if you want to bring equipment into an integrated test facility, you have to adhere to the SATCOM spec. And that way that the host lab facility can actually communicate with your hardware. So we have to meet the same requirements as actually said when we take an SLS in a box to another center, we have to adhere to the SATCOM specs so they can drive our hardware and simulation as part of their test integration activities. So I wanted to make sure to hit on that as well. We're really, right now, our current work is we're really ramped up on doing a lot of the post-test analysis. Like Ashley said and Larry hit on it earlier, is we have so much data now from all these test runs and activities going on. Maestro's really getting involved with kicking off a lot of the analysis tools as part of the post-test, so we can do a lot of the generating the reports and whatnot for the analysis, you know, so there's not a lot of man-in-the-loop activities. We can automate a lot of that, so. But, so you want to say one more thing, Ashley, or I know we're out of time. So.
So, thanks, Jared. I appreciate it. The main thing to note here, besides, you know, it's a really high level, and we apologize, 25 minutes, can't really talk about a full hardware-in-a-loop simulation capability the way you'd like to. But, you know, Maestro has been proven to be configurable as well. We've used Maestro in the X-ray Cal, doing some work with them. We've taken Maestro and ported it into the REST project that we did for the Department of Defense. Same thing with Artemis. So the main thing I want you to take away here is Artemis was built and Maestro was built to support a large launch vehicle program, but we had foresight when we started building the simulation and the test conductor interface to make them highly configurable, because we really felt that we would want to use these two software suites on different projects, small projects, other projects. We do have some desire to make the Artemis framework open source. It's a little challenging when you're 90 to nothing trying to hit milestones for the program, but we are looking at trying to do that. I know Dr. Toby and I have interest in trying to do that. So if you're interested and you're now going, I got to get me some of that, right? Got to get you some of this. Just, you know, get in touch with myself or Dr. Toby or Jared, and we can talk. We got a few moments for questions if you got any, and I brought the heavy hitter in case you had some real
we can
hard
take
ones.
like one question.
No, we got two.
By the way, if you guys want to do a splinter session, if there's a lot of questions, we can definitely do a splinter session across the hall, right? So we've done that before. Questions? Nope. One, Jason has one.
Yay. Okay.
Oh, all right. Yeah, they, okay.
All right.
So we'll.
Just again, Jared had mentioned they're processing a lot of data. If you were on the tour, you heard Paul Hastings tell you that with a 40-minute run, average test run in the lab, we produce over 1 terabyte worth of data. And if you heard me earlier, we can support a 36-hour run. So that'll tell you how much data we're pumping. So the simulation is very configurable. You know, we can change that to data recording via XML to record every second instead of, you know, every 2.5 milliseconds. So we can reduce the amount of data, you know, in that regards. But it's still a lot of data. All right. Thank you.
Great. Thanks. Okay, so if you're a presenter and you haven't signed a consent form and you're getting up to present, go ahead and sign this real quick. It only takes like 15 seconds. So our next presenters are, well, I'm not, Luis. Luis is the presenter, yes.
Let me test this real quick just to see how. Okay, cool. I can't go. Can I go back?
Yes, look at the buttons there.
Yeah. It doesn't.
Not letting you?
Oh, there we go. Okay. So, hi everyone. My name is Luis Rodriguez. I'm a member of the Johns Hopkins Applied Physics Laboratory, and today I wanted to talk to you about some of the technology that we've developed at the lab as part of the DART flight software team regarding FPGA instantiated processor in the loop for flight software development. So it's a mouthful, but it's a very neat technology that I hope to share with you, and hopefully we can you can find some usage for it. So before I even get started, I wanted to thank the team. I'm representing an entire team of other flight software engineers who have made this work possible. So they're up there on the slide. So today I wanted to talk about the DART mission. So this is the mission that pretty much started the technology that we'll be discussing today. And then some of the motivation, the reason why we developed what we developed, are current flight software development testing modalities, which in previous presentations you've heard about WHIL and things like that. So we'll go over those briefly. And then we'll also talk about what DART has done up to this point regarding our flight software in the loop testing environment and our processor in the loop, or PIL, testing modality. And finally, we'll just go over a use case and discuss some of the future work that we're planning to do with this technology. So let's start off with what is DART. So I don't know if you've heard about DART, but DART is the Double Asteroid Redirection Test. It is funded out of the NASA Planetary Defense Coordination Office. And the purpose of it is to pretty much just demonstrate the efficiency and of the kinetic impactor technology. So what does this mean? It means that in the case that we're ever in distress and the planet is going to burn because an asteroid is coming to hit us, we want to have the technology that we need in order to stop that from happening. And one of those technologies is a kinetic impactor, which is kind of, I guess not really to a scientific community, but kind of fancy way of saying we're just going to build a spacecraft to then destroy it against this asteroid and try to change its orbit. So the spacecraft, DART, will be hitting Didymos B, which is part of this binary system of Didymos A and Didymos B. And the hope is that by hitting it, we can change the orbit of that smaller asteroid around this larger Didymos A asteroid. And we can make observations from Earth to more accurately understand exactly what the effects of this kinetic impact are and understand the technology in the case that we ever do need it. So excitingly, there was recently some commotion in the European Space Agency, actually, that now they're funding a Hera mission, which is going to be a follow-up to DART pretty much. So we are planned to impact in 2022, and then in 2026, the Hera mission is going to go to the asteroid and check out what mess we made, right, after we impacted the asteroid. So what exactly does the spacecraft look like? I just wanted to give you a little perspective because it's really cool to me that we're going to be hitting a 170-meter asteroid with a spacecraft that is a little bit larger than a school bus, but a little bit smaller than the Arc to Triumph, and that is with our solar arrays rolled out. Honestly, if you stand in front of it, it fits in this room just fine. So it's kind of incredible, you know, what we're going to be doing here. And the reason why we're hoping this kinetic impact technology works is because we're going to be hitting it really hard, about 6 kilometers per second, which roughly translates to about 13,400 miles per hour. So try getting in a car going that fast, right? So we're going to be hitting the Didymos B, like I said before, and then we have Didymos A up there for reference as well. So in DART, just like in any other I guess, software project, there's usually a project plan with multiple project phases, right? And as we go through these project phases, the problem is that with time, errors that we find later become more expensive, not only in time, but also in money. I guess time is money, so both, to fix. And so what the Dart team wanted to do was, well, we want to make sure that the flight software developers themselves, before we even get into integration testing or anything like that, we want to make sure that the flight software developers themselves have all the tools that they need in order to quickly develop, test, and then once we get to the actual integration testing with the real hardware, we can have a better understanding of, well, this was working on this environment, so now we just need to figure out exactly where things are going wrong when we're trying to interact with the real hardware. So we want to make sure that we're testing in the code and testing phases of our project, right? To make sure that we catch the errors early and we don't spend as much money. Dart also has a unique nature in that it is a shorter mission in terms of time frame. So you need to make sure that you're being agile when you're developing. And this word agile has been spreading like wildfire all over software, including flight software. So this project definitely had a need for such a culture, because it was a fast-paced mission, and we wanted to make sure, you know, we didn't make any mistakes. So in order to provide this development infrastructure for flight softwares to develop their code and test it often, we needed to create, you need different types of development environments, right? And someone had previously mentioned that these different development environments come with different levels of fidelity. And so I just wanted to briefly say that what I mean by fidelity is just how close we are to duplicating the actual real-time conditions of the mission, right? So we're talking about things like endianness, we're talking about things like clock rate, available RAM, and some of the other things that I believe Ashley just spoke about when talking about their wheel environment. So we want to make sure that whatever it is we're testing, we have a good understanding of the fidelity level and the confidence in our tests that we can have when we're developing flight software. So in the DART mission and at APL, and I'm pretty sure a lot of other organizations that work in the space industry, you typically have multiple development environments, right? And we have our spacecraft integration tests, in which we do actual tests with the actual hardware mounted on the spacecraft, and those tests are great. But newsflash, if you're doing your first test of line 272 in your some C file during your spacecraft integration test, you're going to have a lot of trouble. So there has to be something else, and that something else is typically WHIL, which is the test bed or hardware in the loop, right? And Ashley, like I said, just talked about WHIL, but what we noticed, at least in DART, was that there had to be something else that we could provide to the flight software developers so that they could quickly check their code. And so we came up with what's called software in the loop, which we actually had a presentation about in last year's flight software workshop, but I'll briefly go over that in just a few minutes. But then that still wasn't enough, because there's some sort of gap in between the two in terms of fidelity, in terms of testing fidelity. So we wanted to bridge that gap, and that's pretty much what we're going to be talking about today. We're going to be talking about PIL, which is processor in the loop. So let's now dig a little bit into each one of these things and how they differ from each other. So just to quickly go over what exactly our hardware in the loop is you have avionics and real-time simulator. So I honestly feel like a rock star with this thing and the microphone. But so what we're talking about in terms of hardware in the loop is avionics and real-time simulator, where we have testbed software emulations for each one of the hardware that we're going to be interfacing with in the spacecraft, right? And as the project goes on, hardware gets delivered, like everybody has been saying, hardware gets delivered, then we can switch out that those emulations with the real hardware, and the fidelity of that system then increases, right? Because we're actually testing on the real hardware. However, this starts to happen only when hardware starts getting delivered. So you don't want to be, as a flight software developer, stumped by the fact that the hardware has not been delivered. So that's why we have those testbed software emulations, right? But the problem with the testbed software, the testbeds themselves, is that they're typically very expensive. All the developers want one because we want to make sure that we're testing our code as often as possible, and so there has to be a schedule maintained and all these things, which make configuration and maintenance kind of difficult. And finally, the initial state of the testbed is usually unknown, because if I test my code today and at 3 p.m. somebody else has it, you have no idea what configuration I left it in. So all these things together make up hardware scarcity, right? Now there's a limited amount of test beds that we have, and we still need to get a lot of code done. So what the Dart team created was the software in the loop, which is pretty much what we like to call a spacecraft on a laptop. You need nothing else except from Docker and then all your source code. And so what this is, some of the enablers that allowed us to do this were the Core Flight Executive, as developed by NASA, the Cosmos by Ball Aerospace, and finally Docker. And I didn't put by Docker because it's the same name, but Docker by Docker, I guess. So let me talk a little bit just about what these two last things are, and then we can dig into the real meat of the presentation. So Cosmos is our micro mission operations center. It's what we like to call it. So it allows us to have commanding and telemetry of the spacecraft on our laptop. It is an open source project. It's pretty great. And it allows us also to test everything and automate all of our tests within this Swill spacecraft on a laptop environment. So that's pretty much what we're using as our micro mission operations center. Then Docker, just out of curiosity, have any of you heard of Docker before? Yeah. Oh, awesome. Okay. So I'm still going to say what it is. Docker is a containerization tool. So it is easier with it to create, deploy, and run your application, right? And so the way that I'm going to be using these terms throughout the presentation, so I just kind of wanted to clarify. The way that you can think of a container is kind of like an application or service package that has everything that you need in it. It is kind of like a VM in that you have complete isolation of your environment within this container. However, with Docker and with containers, what you're actually, the abstraction layer is on the OS and not on the hardware like it typically is with a VM. So this makes them a lot lighter and makes them easier to just instantiate and tear down. So we use those in our Swill infrastructure and also in our processor in the loop infrastructure, as you'll see. Then we have images, which pretty much define our containers. So it has configuration pretty much of the environment that the container is going to be running in, and then a Docker file which defines that image. Finally, there's something I didn't include up there, but there's Docker Compose, which allows you to create a network of these containers and have them communicate with each other, which is what allows us to do our spacecraft on a laptop, right? This network of different containers where we'll be discussing what each container would look like. The final thing we noticed is there's going to be a lot of different things that need to be very well configured. So we needed some sort of standard, I guess, directory infrastructure. And so we came up with this, where the developer just needs to install Docker, clone this flight software Docker repository, and then this flight software, the Docker repository has everything that you need in order to instantiate the spacecraft. It includes the Docker Compose files, which define that network of containers, the Docker files, which we just discussed, utilities, and a shared environment. This is the star of the show, shared environments, because the shared environments is pretty much where we have all of our submodules, and I'm sure we're all, or hopefully we're all familiar with Git and versioning with Git. So submodules, we can plug in all of our submodules into this main repository, and like that we are pretty much, it allows us to plug and chug different source code. So for flight software, for the testbed software, for Cosmos, which is our ground system, we have up there a workbook translator, which allows us to, from XLS, create databases that we can use in Cosmos, and we can actually translate those same XLS workbooks then into like something that we can use in L3. So the purpose behind this was so that in the future, as other missions try to use this environment, they can just keep everything else except for whatever is Dart flight software, unplug that and plug whatever they have in, right? So tried to make it as modular as possible. So I wanted to take a look, just a little closer look at Dart flight software specifically. So obviously this would live under flight software Docker, shared environment, Dart flight software. And then if we take a look inside that, what we have is two different paths or compilation build paths, right? And so we have one that's for Spark UT700 RTEMS and another one for PC Linux. And so what this allows us is from the same code that we have in that whatever Dart flight software submodule is, we can create two images. One image that we can deploy onto our test beds to Whill, and then another image that we can deploy to run our spacecraft on a laptop. So once you've done that and you have compiled images, then you just instantiate your spacecraft. And so the actual container network looks something like this, where you have your flight software container interacting with your testbed software container back and forth, and then your testbed software container interacting with Cosmos. And Cosmos provides a display to the user so that they can run their tests, they can command the spacecraft, and look at telemetry coming back. So the reason why I have these kind of like on cylinders is because each one of these, the actual code is volumed into the containers, such that, I don't know, I mean, most of you are familiar with Docker, so you know that you can copy code into these Docker containers, right? But the problem with that is that once you've copied it in, that means that that Docker container is going to have that set of code. So what we wanted to do was make sure that when we instantiate the container, we can look at the code immediately just through, it's whatever's in your machine, right? And so what volume encode is, by the way, if you're not familiar with it, is that you can actually access the directory from your host machine from that container. So that's pretty much what we're doing. So what this gives us is something that's cheap. All developers can have one because it's just on a laptop. It literally runs on just your laptop. Its configuration and maintenance is simple, mainly because you don't have to worry about it much. And the initial state is known because you always know that once you've teared down that stack and you bring up a new one, it's going to be brand new. So this makes for faster, reliable development, right? But what's the problem here? The problem is that we're not running on any actual hardware, so then we have lower fidelity. And what we're trying to do is keep at least some level of confidence in our testing. Of course, Swill does provide some level of confidence in that just normal things that you would test on your flight software development, very rudimentary things. But if you want to test on a more highly fidelic model, you need something that's in between a test bed and flight software, right? So what we decided to do was, okay, well, we created this beautiful modular infrastructure. So what can we do? Well, we want to keep Cosmos for the user to interact with the spacecraft, but let's replace the flight software container and let's plug in some real hardware and plug that hardware into our computer, and then now we have this processor in the loop infrastructure which allows us to just run on real hardware, or at least hardware that gives us a higher level of confidence whenever we run our tests. And so the question now becomes, well, I mean, what hardware could we possibly use for this, right? And it just so happens that as we were working on this, there was another team of very bright engineers at APL that were working on, well, let's try to find something that's a little more inexpensive to get something similar to where we actually run our flight software, right? And so what they came up with was Smart Fusion system on a module. And so it's practically just an embedded software Leon 3 processor programmed into an FPGA. And it's a variant of the more expensive Leon 3 boards that we use to run our flight software on the test bed. So, 5 minutes? Okay. So this allows us to connect via Ethernet and USB. I might have to speed up a little bit. So what this allows us to do is it gives us a more loyal environment, right? Something with more close clock rate, endianness, and real times, which we don't get from Swill. What that hardware team also did was they created this custom bootloader and netboot image that allows us to load and run the image without Gurmon, and it allows us to update the image without having to worry about Gurmon either, because all we have to do is pretty much just we drop it into a directory, and the processor immediately knows something changed there, so it'll reset itself. And then all configuration setup is what they didn't realize that they were doing is they were making it very, very easy for us to configure and set everything up using Docker, because if it's just as easy as moving files around, Docker can do that, right, on runtime. So we decided, okay, let's mix these two things, and then we have pill. So what that looks like as a change in your file infrastructure is now you just have, in that same Dartflight software directory, you now have a path for the Smart Fusion image. So now you can build 3 kinds of images that you can deploy, where the Spark Smart Fusion RTEMS image is very much like the UT700 one. And so what does this get you? It means that you can get from something like this to something like that, just running on your desk, right? And you have you keep that level of fidelity. So something else that we're achieving is we're bridging that gap. So now we don't have that gap in fidelity, right? You can choose swill, you can choose pill, you can choose will as the project matures and as you go through the phases of the project, which is what you want to do. You don't want to slow down because you're waiting on something else. You want to continue to develop. Now the question becomes, well, then why use swill, right? I mean, I could just use pill, so why use swill? Like, what's the purpose of doing that? So, well, the purpose is with pill, you get a higher fidelity model, but if you want to instantiate something quickly, and if you want to have a bunch of them in your machine, you can use swill, because with pill, you're limited by the single FPGA. But of course, usually when you're developing anyways, you want to just test on a single, you're testing on a single spacecraft. It's not like you want 50 of them on your machine, although you can run 50. I mean, maybe you want to hit the asteroid 50 times, but there's still some win on both sides, right? And the point is that you have that array, you have that choice to make as you develop. So what this allows us to do as well is that we can integrate all this into our continuous integration pipeline. So in Dart, we use Bamboo, which is pretty much just a continuous integration orchestrator, I guess you could call it. And it allows us to run a bunch of flight software tests, unit tests and app tests. These unit tests are on the code, obviously, and then the app tests would run using the Cosmos test runners, which allow us to send commands and expect some telemetry back and do application tests like that. And now we're not only doing it on swill, we can also do it on pill, on the real hardware. And how we do that is we have different, wherever the Bamboo agent is running, we plug in a pill, and then we run on our pill environment. So in the future, what we would want to do is grab a bunch of those and create a Bamboo army where we just have Bamboo agents everywhere with a pill plugged into them, and we're just running tests every single time that some sort of software change is made. And we already do this with swill, but we would be increasing our fidelity with pill. So we want to make sure we work around some of using Docker tools, which if you're interested in, I can talk to you about if you approach me, because I'm running out of time. I have 1 minute. Okay, so and we hope that other missions start adopting the technology as well. Finally, I'd just like to thank the NASA Planetary Defense Coordination Office for funding us and saving us, hopefully, in the future. APL, the DART team, and the Flight Software Workshop for inviting me here. Honestly, it's a pleasure. I love the wire because I feel like a rock star, and I'm talking about something that I'm passionate about. So if you guys have any questions, let me know, and if you want to approach me at any point, feel free to do so. Yes, it will transfer kinetic energy to the dynamos. You said between an FPGA. I don't think the mic is on. So between the FPGA and what? Honestly, the reason why we decided to go with this is because there were efforts at APL that we had already undergone, and so we wanted to adapt that technology. And also the NetBoot loader image made it really easy to integrate with Docker. So that's pretty much why we decided to go that route.
Other questions?
I just want to say I have a presentation that's after the next one, and it's about a QEMU-based processor in a loop test bed. Woo!
Cool.
Get the best of both worlds.
Other questions? Nope. Great. Thank you. All right. So our next presenter. Like they're getting ready. So just glance over at me every now and then, because I'm going to keep time for you. I'll let you know when you get the 5 minute, or you next presenter, the 5 minute mark, and then I'll count down. And try to leave a couple minutes for questions if you can. If you haven't signed the form, all right, good, thanks.
So, hi, my name is Stefan. I'm a software engineer, and I'm responsible for the software development of the Destiny Plus dust analyzer instrument, which is part of the Destiny Plus mission. I'm working on the Institute of Space Systems in Stuttgart in Germany. It's in south of Germany. The institute has about 150 researchers with different fields of research. For example, astronautics, space stations, chemical propulsion, satellite technology, and cosmic dust. So we heard a lot of about processor in a loop, hardware in a loop, software in a loop, and now I want to give you an overview of about the requirements in a loop approach. Maybe none of you heard about it. Okay. So I want to give you a short overview about the Destiny Plus mission. Then about the challenges and the characteristics of requirements engineering. And then I want to show you the requirements in a loop approach. Okay. So Destiny Plus stands for Demonstration and Experiment Space Technology for Interplanetary Voyage. It's a Japanese mission. And we, as a German institute, deliver the Destiny Plus dust analyzer instrument. So the Destiny Plus mission is an upcoming deep space mission. It will be launched in. The plan is to launch it in 2022. Mission period is a minimum of 4 years. And it has an ion thruster as a propulsion. And the goal is to do a close flyby at the active asteroid Phaethon. And the Destiny Plus dust analyzer is a major part of the scientific payload of the mission. The Destiny Plus dust analyzer instrument is able to measure cosmic dust. That means it can measure interplanetary and also interstellar dust. So it has a high resolution time of flight impact mass spectrometer. And the instrument is derived from the heritage of other dust instruments, like the dust instrument on Cassini, Giotto, Rosetta, and Stardust. And DDA, that's the short term of Destiny Dust Analyzer, will measure mass, velocity, electric charge, and elemental composition. Okay, one slide about Phaethon. The Phaethon is the parent body of the Geminids meteor shower. It's a B-type asteroid. And what's special about Phaethon is the asteroid is active, but the mechanisms are still unknown. The mission goals of Destiny Plus are to do a flyby and to measure the dust ejection, to measure the dust composition, dust distribution, to measure interstellar dust, and we also want to measure interplanetary dust at the Earth environment. Okay. So I'm responsible for the flight software. So the flight software of the instrument has some functionalities. For example, to process the science data. For example, do some compression and onboard analysis, to handle the housekeeping, to communicate with the spacecraft. The software has some interfaces with onboard FPGAs, and yeah, it also has to configure FPGAs, control of the pointing mechanism of the instrument, because the instrument itself can move, and yeah, to handle the mode of the instrument. the challenges of the development of flight software are we have little reuse, and it's a unique development. The software maintenance is difficult, so we have also a late availability of the final platform. The software is critical for the mission success, and we also have a long development cycle. So that means we have to focus right at the beginning, from the beginning on, we have to focus on requirements engineering. So what's the challenges on requirements engineering? The challenges are often there are missing resources and know-how to specify good requirements. I will show you what it means what good requirements means. That leads to frustration in the project, notably testers. The maintaining is difficult of the requirements itself during the project phases. And there's also a lack of communication within the development team and also to all the stakeholders in the project. So I would like to give you a quote from a paper I found. And it says, finding and fixing a software problem after delivery can be upwards of 100 times more expensive than finding it and fixing it during the requirements and early design phases. So you can see on this chart that when you create a problem on your requirements, it can be very, very expensive in your project. Okay. So what's the characteristics of good requirements? Good requirements means that your requirements are correct, that your requirements are consistent, unambiguous, legible, complete, and testable. So I thought about it, and as a result, I think good requirements are difficult to create manually. So our approach is to do requirements in the loop testing. So we have you see hardware in a loop, software in a loop, and model in a loop. And requirements in a loop can fill the last gap on the development cycle. So we want to verify requirements as early as possible in the project. So our approach has two elements. The first one is to provide a practical and scalable approach to formal requirements. So there's the challenge that formal requirements have to be understandable and precise. And our solution is to use a combination of textual and graphical notation for formalization. So we model textual requirements using readable language templates. And we model state-based complex control logic via state machines. The second element is that the formalization enables an early verification of requirements. That means validate requirement against expectations before developing the system. So you simulate your requirements before you start to write the software. We use a simulation to discover incorrect, ambiguous, missing, or incomplete requirements. And we use randomized stimuli to find incorrect requirements. Okay. So I want to show you our workflow. Step one, we describe our requirements. So you can see on the first picture how to model textual requirements by using readable language templates. For example, in the first line, it says every 1 second when the current angle of the instrument is smaller than the commanded angle, then the pointing shall be changed, and it shall be changed about 0.5 degrees. So that's the formalization of one requirement. On the next image, you can see how to model state-based complex control logic via state machines. So it's not. It's also possible to use some graphical notations to describe your requirements. There are several tools on the market who can do this. We choose the tool Stimulus for our requirements in the loop approach. Step 2. We put our formalized requirements into a test bench. Now we're getting to the step where we can do the requirements in the loop testing. We have some stimuli for the requirements, and we have an expected output of the requirements, an expected behavior. We call it observer. And within this test environment, we are able to simulate our requirements. So it's also possible to import the software itself on the next step. So you are able to verify your requirements against the real software. So you get a complete traceability in your development process. Step 3, simulate and analyze your requirements. You can see a waveform. That's a result of an example of a result of a simulation. You can see the different time steps and the different values of one signal, and that enables the possibility to get to see very fast how your requirements behave. And it's also a good possibility to show this to other stakeholders, and it's a good basis for a discussion. The last step, step 4, discuss and refine your requirements. So the tool itself, the tools are able to detect if there are some consistent problems in your requirements, or if your requirements are not, their requirements are unambiguous, and it can be done automatically. But if the requirements are correct, complete and legible, has to be discussed with your stakeholders. So this enables the possibility to discuss it within the software team, with the project manager, and with the customers, and so on, with all the different stakeholders. Okay. The benefits are you achieve early requirements validation in your project. You increase the quality of your requirements. You increase error detection in the requirements. You improve requirements maintainability, because you can make very fast some changes in the requirements. You can check automatically if your requirements are still correct and consistent. You can share clear requirements among the different stakeholders in your project, and it's also possible to reduce language barriers. especially in international corporations. Okay, so the conclusion. Good requirements are difficult to create manually. Faulty requirements can become very expensive. Formalization enables early verification and validation. Requirements in a loop can reduce failure probability in your project. It can be used for failure investigation. And requirements in a loop is especially suitable for functional requirements, especially for application software, for software with timing behavior, for clear inputs and outputs, and also for requirements for critical software. So, in my opinion, it's not good to simulate all your requirements. For example, when you have non-functional requirements, it does not make any sense to formalize them. Sometimes it does, but not always. But you should focus with the requirements in a loop approach on your critical software parts with timing behavior. Okay, thank you.
Questions? Yep.
Well, since you have already formalized your requirements to a certain degree, are you also considering to using these requirements for further model transformation to actually generate any software?
I don't get it, sorry.
Do you also use your formalized requirements to generate software?
No, not yet. That would be the next step. What it's able is you can generate test vectors based on your requirements. But that's something we already we thought about, which is maybe possible. But then you have the problem that you have one basis, it's your requirements, and you generate your tests based on these requirements and also the software. But so you have to really make sure that your requirements are correct.
Other questions? Nope. Sound like you have a tough job. Thanks. Thank you. All right, our next presenter. Oh, wait, we have a break. That's why he has that up there. Okay, yeah, we have a break right now. So we'll be back at 10:30. Thanks. If you haven't signed the release form, if you've presented, please check the registration desk. Thanks.
it's going to take some thinking, because I was thinking I was presenting earlier. I actually walked up and recorded it. I might do that. That's what I was thinking. And I'm like, well, oh, yeah, yeah, yeah. It must be something. Well, yeah, no, right. I think I have to start with apology for doing it.
We're going to go ahead and get started. Looks like people are slowly coming back from. Our presenter is Kevin Rowland. So go ahead, Kevin.
Sure. Thank you. Can you guys hear me okay back there? Okay, good, thanks.
Can I make one comment?
Sure.
So one of the comments from upstairs is if you're a presenter, try to keep the mic at a constant distance about 3 inches from your mouth because they're having trouble upstairs. They have to keep adjusting the volume.
Sure. Thanks. Hi, everybody. My name is Kevin Rowland. I work at the Aerospace Corporation in El Segundo. I mainly help to build hill test beds for a few different launch vehicles. Spent some time writing software for a CubeSat program, and earlier this year, around March, I was writing flight software for a secondary payload that was slated to fly basically as an experiment on a larger vehicle. That was aerospace, designed, built, and operated. That program was kind of the genesis, excuse me, for this work that I'll be presenting today. Gonna skip the agenda real quick and just go to basically the bottom line up front. Really, it was just in just a week, a team of engineers at Aerospace spent that time building a proof of concept of a closed loop test bed, but using QEMU, which is an open source machine emulation framework to host an emulated flight computer. The 1 week is important. We actually only had 1 week to finish the work. It was funded by our internal innovation lab, basically. The iLab sponsors these so-called sabbaticals. They're short duration projects for engineers to basically demonstrate the feasibility of a new technology. So it was a sprint to the finish. And we had some good results, hopefully. I'm going to start basically just by talking about QEMU. You've heard a little bit about QEMU, I think, from other presentations, in particular the high performance spacecraft computing folks from OAR. But I know some of you probably aren't familiar with it, so I'm going to try to give a little bit of a more technical overview of the technology. QEMU, as I said, is an open source machine emulation framework. It provides software models of most processor architectures, the more popular ones definitely. You might be familiar with QEMU in the context of a virtual machine, in which case it provides the ability to hook into something like KVM from Linux to emulate multiple machines running on one, for example, desktop class x86 processor. But it also supports so-called cross-platform emulation. That's basically where the host target is not equal to the guest target architecture, in which case it provides functional emulation of the machine, right? But it has to go through essentially a bytecode interpreter, so you're not actually running with cycle accuracy. And that instruction is done basically by another open source project called the Tiny Code Generator, which was folded into QEMU for runtime bytecode interpretation. It supports a variety of architectures, as I mentioned. I wanted to take the opportunity actually to look at the bytecode interpreter really quickly, just to kind of expose the fact that this isn't really magic. It kind of feels like it when you're running QEMU. On the left here is some thumb assembly code, ARM assembly code. It's actually taken from the flight software for the payload I'm talking about. This is actually the first non-branching instruction that's executed after reset. And if you go into the ARM architecture reference manual and you find the opcode, it's right here. And if you guys can read that, I know it's a little small, you can dig into QEMU and watch as the translator walks through the opcode bit field by bit field, basically, in order to get down to an eventual operation on the emulated CPU. I thought that was kind of cool to look at how it does this this translation from one architecture to the other. I know you folks know this, but it bears repeating, I think, before we start talking about developing peripheral models for this emulated machine, that an SoC, a system on a chip, is basically just a big memory map, right? For our particular machine, it was a ARM Cortex M0 based system on a chip. The Cortex M0 part of the emulation is fleshed out in QEMU. It's already supported. We didn't have to do that. We definitely couldn't have done that, let alone in the span of 1 week. So what we needed to do was basically capture memory reads and writes to peripheral hardware addresses, right? And to mimic the side effects of those peripherals. One thing that you got to keep in mind is that when you're mimicking the side effects of peripherals, in particular, low speed or simple serial peripherals like UART, I2C, and SPI, is that you can't necessarily pass those transactions down to the host operating system like you can if you were writing to video memory or something, in which case it would be passed down to the host video controller. So here's a little contrived example of basically just a UART write, right? You might disable the UART peripheral, stick some data in its transmit FIFO, enable it, and in real life, here's what happens. There's a side effect, there's a physical side effect. A wire gets wiggled, and on the other side of the wire, someone can catch that UART transaction and ingest the byte. When we're modeling our hardware peripherals, we can't exactly do that, right? We're constrained to a desktop Linux machine. We're not going to wiggle any wires. We're trying to emulate what happens with a UART transaction. So we have to think about how do we get that byte off of our emulated machine? Where does it go, and who can kind of capture it, right? So that's QEMU. I'm going to talk a little bit about this emulated processor in the loop test bed. It's good timing today to come after the talk from APL about the PIL with the DART program, because that was a really good explanation of kind of what a hill looks like, what a sill looks like, what each of their pros and cons are, and what kind of a middle ground would be in between the two. So I'm going to repeat a couple of those things, basically. With an emulated processor in the loop test bed, you get this really big capability, which is you can run flight-like binaries on the emulated processor. Okay, so you don't need to do any surgery on the software in order to adapt it for commercial x86 machine. But you do avoid the high capital cost of real hardware, similar to the way that I think the Leon 3 was instantiated on an FPGA with the APL presentation. That's a little cheaper than getting real hardware. In this case, it's QEMU, it's open source, it's free to download, free to distribute, free to modify. So you get to maintain the ability to test like you fly, because you're avoiding flight software modifications, but you get the benefits of working in a pure software environment. The other advantages to an emulated processor in the loop test bed are that because you're running on a single Linux machine, it allows you to run multiple simultaneous simulations, right? The DART team talked about this too. When there's hardware, you have one piece of hardware, everybody contends for it, and not everybody gets to test when they need to test or what they need to test. With an emulated processor in the loop test bed, you kind of overcome that challenge. This is a quick look at kind of how an emulated PIL sits in between a hill and a sill. The trades are probably more nuanced than this when you get to wondering what test bed you might want to make for your program. At Aerospace, we make test beds for a variety of programs. We're on contract basically for independent verification and validation. So we have to make these kinds of trades often when we're drawing up contracts or we're deciding what to do for a particular program. But I'm not going to go into real detail here, but you can see that an emulated PIL sits in the middle in that it allays some of the issues with a hill and with a sill. So now I'm going to get to our actual project. That was just QEMU, the technology, and emulated processor in the loop test bed, the technology. But what did we actually want to do, right? Basically, we wanted to use QEMU to model an ARM-based Virago VA10820. Virago Tech is a company out of Austin, Texas that makes radiation-tolerant systems on chip. In order to build a PIL test bed for the Spacecraft program I was talking about, which I can't talk too much about, and potentially because we might use this processor for our AeroCube CubeSat program. So we took modified control software, originally developed for that Spacecraft program, and we wanted to run that on the emulated processor. So we had to think about what do we have to fill out in the emulation so that the software runs unmodified and it thinks it's actually operating on an actual Virago. There was one small modification. It wasn't surgery to overcome the limitations of running on a sill or to rehost the flight software. Basically, all of our communication was over SPI. We decided to take one of the functionalities of the software and put that on an I2C bus instead, simply so that we could build out the I2C peripheral in the system on a chip in QEMU and exercise that peripheral. And then we use an existing vehicle simulation. It's called Frames. It's just an in-house simulation framework at Aerospace to provide the 6DOF vehicle model, basically, and simulated sensor measurements to close the loop. Here's the actual system on chip. Here were our goals. Some of these slides were from the proposal to iLab. So we're speaking kind of in the future tense that these are goals. We hoped to emulate these three, low power, simple peripherals because they would actually be used on the real flight software. And we were hoping we might get to something like timer emulation. We didn't. And here I've highlighted exactly kind of what we're going to do. We're going to want to write peripheral models down here to act like we're the hardware sitting at the end of the system bus, basically, reacting to register reads and writes and having some kind of side effect. What we want to do then is if there's a write from a SPI peripheral, we want to bridge that write over to an external simulation so that the external simulation can update its state. If there's a read from a peripheral model, then it needs to read data that has previously arrived from the simulation. That's the closed loop aspect here, of course. One thing I want to talk about a little bit, I don't know how familiar people are with QEMU. There are I2C bus emulations in QEMU. It's all baked in, but really what happens is when you write to an I2C peripheral, emulated peripheral in QEMU, and it gets put onto the emulated I2C bus, that all stays within QEMU. So you can talk to other devices that you might have defined in QEMU, but it doesn't really allow you to, punch out of the emulation and into the external world, which is what we needed to do because our 6DOF vehicle model sits somewhere else. It's a separate application. It runs separately. Could be running on a separate machine. It could be running right next to you on the same machine. But either way, it's not in QEMU. So we had to think of a different way to get this data out of QEMU's virtual machine. That's just another little overview, a little cartoon overview of what we're trying to do. And you can see, that we're wrapping it in one in that large box, which is just one single Linux machine. And that helps. All right, so what did we actually do? Well, we wrote some peripheral models as planned. We really just made it to the bare bones functionality. It was enough work to kind of dig into QEMU on a Monday, try to figure out how this large code base works, how to plug into it, so that by Tuesday or Wednesday when we were actually able to issue reads and writes from our flight software running on QEMU and see that they were actually making their way into our stubbed model, we didn't have much time to actually fill it out, but we filled out what we needed to, which is, enabling, disabling the peripherals, allowing for the transmit and receive FIFOs to be filled and flushed, right, from flight software. And that was for our UART peripheral, our I2C peripheral, and our SPI peripheral. I put some code on the side here too. It's small again, but it is always nice to see. I'm not going to go through it in detail right now, but if you get a hold of the charts afterwards, you can kind of look at it. You can also go into QEMU source code, of course, and look at how people model peripherals. Peripherals, obviously, they just hold some state. When a write transaction comes down to the peripheral register address space, the state might be mutated. The peripheral might have some side effects. That's basically what happens down at the hardware level, and so we need to emulate that. We needed to emulate that in QEMU, and we were successful in doing so. This is just a little, I've gone over this, that each of the three peripherals are used basically to communicate with the external simulation. This is a more detailed description of what exactly they do. The I2C bus was for transmitting motor commands to a gimbal, which was accomplishing pointing. SPI for receiving encoder measurements from the same motor, so you could close the loop and have your control law actually close. And then UART was to receive ground commands, simulated ground commands, which allowed you to set a new set point. So you could see during a simulation run that setting a new set point resulted in the control law reacting and driving the motors to that new set point. That was a good way for us to show that we had accomplished what we wanted to accomplish in tying everything together. Okay, this was some of the more interesting stuff. I think one of the difficulties we had when we were writing these peripheral models. We decided basically to take any side effects that occur down at emulated hardware, package them up, bundle them up, and basically push them over UDP to some external user. Didn't matter who it was, whether it was some software just gathering the data to log it, or the actual 6DoF vehicle model on the other side. One thing we were interested in is basically minimizing UDP traffic, right? We don't want to react to every single byte that enters the transmit FIFO of a UART peripheral or an I2C peripheral or a SPI peripheral to result in a UDP transaction. That's a lot of wasted effort, basically, when you're sending long strings of bytes over a UART peripheral. So you want to think of some communication heuristics, right? When do you decide that your transmit FIFO is full enough that you want to package that up and send it over to the external simulation? For I2C, it was really easy. The I2C specification actually talks about, the ability of the transmitter and the receiver to know the length of the transaction beforehand. It uses an explicit start bit in the command register to kick off a transaction, and an explicit words data word in another register in the peripheral to tell it how many words it should expect to send or receive. For the SPI peripheral, it's a little more difficult. You really just send bytes down to it, and they're supposed to, in real life, obviously, just wiggle the wire, and they're sent off to the other side. Luckily, we had this mode in the SPI peripheral called block mode, which accomplishes something similar to the I2C peripheral, which is that you can tell a SPI peripheral to wait, hold off, until the transmit FIFO is full of a couple of different words. Then you can tell it to start. It'll send all the words at once, and we use that to our advantage to minimize UDP traffic. And here are some results. I think we'll probably kind of blow through these, but they were a good way for us to show to our funders, iLab, and to our management that what we were doing actually worked and that it might be useful for a closed-loop test bed in the future. I mean, there's not much to look at here. The control software executed its algorithm correctly. We could send new set points. So a new set point was sent around here. You can see the control software, I think it was just a PI loop, overshoot, and come back down to the new set point, given encoder measurements from the 6DoF model. This is kind of just a repeat. Set points received from the ground, proof that the emulation worked as expected, proof that our peripheral models worked as expected. We didn't have to modify anything in flight software that actually talked to the real peripheral models. We didn't have to modify any of that in order to actually send data from our emulated peripheral models. So that was good. And then this proof of concept of a way to bridge from our emulated peripherals onto the host machine's network in order to send data off to an external user. Okay. This isn't working. Could I go to the next slide, please? Next slide. Can someone? Yeah, thanks. Is it? This is the last slide. This shouldn't be the last slide. I can talk though. Uh, uh, did it jump? Yeah. So there. Good. Okay. There are more slides. I hope. All right. Um. Right. So some more cool things we demonstrated. One of the advantages of using this emulated processor in the loop, right, is that you don't have to contend for hardware. You can run multiple simulations at the same time. If you want to do many dispersions at once, if you want to run Monte Carlo runs, you can do that. But again, you're running on modified flight software, which is nice. We demonstrated that. We had some hokey solutions for doing that, but that was just due to time constraints, things that you could pretty easily manage to fix in the future. Good. Okay. So some future work. We left a lot on the table in terms of emulating the Virago system on a chip fully, right? We focused on those 3 hardware peripherals so we could get data running back and forth between the emulated machine and the vehicle model. So we need to do a lot. We need to do a little bit more of the system configuration or emulate more of the system configuration. The Virago exposes a variety of special registers to control its state or how it operates. We did not get to sending interrupts up to the emulated CPU core, but there's a framework in QEMU to do that. It looked a little daunting. It was Thursday and we didn't have time to do it as we were wrapping up and generating some results, but that would be next, I think, on the table. Same with GPIO. I think it was relatively simple. If you want to send discretes or bilevels out to an external simulation, you need to model your GPIO peripheral to do that. Timers and counters are really important, obviously. If you have, we're running a bare metal with no operating system, so we have a big event loop timed off of some periodic, I think 10 hertz timer. We weren't able to emulate that, so we had to tweak the existing flight software a little bit. Oh, sorry about that. Actually trying to go back, there we go. I talked about this a little bit. I had a whole slide for it just in case there was some more time. But there's this open question: when do we package words for transmission over the over UDP? We don't want to do it that often. A similar analogy is with something called a VM exit, which is an instruction for virtual machines to basically exit out of their code, go down to the hypervisor, and allow the hypervisor to do its thing to switch between virtual machines. There's been a lot of work in QEMU to minimize VM exits. They're costly, right? It's a similar thing here. We know UDP transactions are a little costly, so we'd rather not be doing them for every single byte that hits the peripheral. I'm going to speed through these. I have 2 minutes left. Future work would be actually potentially containerizing this entire test bed with something like Docker. I don't have any experience with it myself, but because it's pure software, it's doable. It means you could send it up to the cloud potentially. You could run it on a variety of servers. And that's a real useful thing when you're trying to test your software exhaustively. There's some future work with, actually speeding up the sim. We weren't able to tell if we were running faster than real time. We weren't able to tell if that would still be the case when we had emulated timers firing at, at virtual 10 hertz. But we can do some things in Linux to basically speed up the application. And then I think this big bullet point's really important. Obviously, do we run faster than real time is important, but do we run proportional to real hardware? We're kind of selling this as an emulated processor. It should feel like the processor. Do our algorithms take approximately the same percentage of our allocated control cycle, whether we're running on real hardware or emulated hardware? We don't know. That would be a good analysis to do. And then, is it worth it? Remains to be seen. This is kind of an aerospace-specific slide. We do a lot of program work for a variety of programs. We have to decide to what level of fidelity we want to actually test contractor software. So we have to think: do we want to buy a development kit and just kind of fake things out that way? Do we want to build an emulated processor in the loop, or do we want to do a pure software in the loop test bed? With some of these cheaper processors, it's obvious. You just buy the development kit, get the hardware. You can get 10 of them or something for your testers, and then install some open source tooling. If you want to test like you fly with something more expensive, something a little bit more difficult to obtain, the emulated processor in the loop might make sense. And that's it. Yeah. Thank you.
Do you have any questions? Questions?
So I just have a clarification question. So you are running QEMU on a virtual machine then and emulating a board?
Sorry, could you repeat the question?
So you're running QEMU in a virtual machine, and you are saying that it's running faster than real time?
So it's not running in a virtual machine. QEMU is creating a virtual machine. It's running as a user space application on Linux, and it's just mimicking the entire system on a chip. That itself is the virtual machine. There's no additional layer.
And it's running faster than real time?
Correct, yes. Faster than real time, right? Because our desktop Linux box that's running QEMU is running at 1.5 gigahertz or something. And this small Cortex M0 based system on a chip runs at, I think, 200 megahertz. So we can blow through a ton of ARM instructions in less time than it takes for the real system on a chip, simply because our Linux processor is so powerful. The QEMU is well done, honestly.
Thanks.
Mm-hmm.
Thank you.
Yeah.
That's all we have time for.
Sure.
So our next presenter is Mark Suter.
Okay, good morning. First, I did want to give a shout out again to the sponsors and the organizers. I really enjoy this conference. I tend to think of myself as a very technical person, and there's a lot of great technical content within this conference. The other thing, I probably should apologize at the beginning. You might get a little whiplash in a couple places from what I'm about to present. I got put into the simulation, software simulation, hardware simulation area. I kind of noticed on the whole set of presentations, and that's normally what I've talked about in the past when I've been here. But this time, as you can see, I'm actually talking about, and I know it's the flight software workshop, but I'm actually going to talk a little bit about ground software. So with that, see if I can. So again, a little more whiplash. I was going to go back to who we are, what our group is that actually did the development of SDF1 and the ground software. So we work for NASA. I think everybody's familiar with that. We're at the NASA software IV&V program where we do software independent verification and validation, primarily for NASA, but also for a few other missions, some NOAA missions as well, some closely related things. We've been ensuring primarily NASA Class A mission success since 1993. So we're talking anything manned. IV&V's been done on ISS shuttle when it was around. It's on all the parts of HEO now. And then also, in addition to that, all the really high dollar NASA missions, James Webb, Parker Solar Probe, those types of missions. The facility and the people there do full development life cycle software, requirements, design code, test, etc. I put and related system because in this type of industry, there's no way you can look at software without really thinking about the whole system. I think our keynote speaker mentioned that this morning. And then so within that, I actually work on a team called the J-Star ITC team. And those two terms are sometimes used interchangeably, which is a little confusing. But essentially, the independent test capability team, we provide the personnel for the J-Star lab to actually develop simulations. And that's what ends up getting used by the other people at IV&V to actually do their job, to do testing with often the actual flight binaries. We do a lot of instruction set simulation and that sort of thing. We also have done emulation, flight peripherals, buses. We just heard a talk about QEMU. We've done a lot of stuff in CIMIX in the past. We're doing some things now in QEMU as that's becoming a big viable platform for us. And we do a lot more. So the basic thing our group tends to do is take the whole system in the satellite and put it on a laptop. So that's kind of the generic. So now back to the whiplash again. So what I was going to talk about though is the actual mission ops stuff we did for our CubeSat simulation of Flight 1. So this was a 3U CubeSat. The primary objective for our group in particular was to develop the NOS Cube simulator. And I think that's been presented several times at the workshop in the past. And so that's kind of the tie-in with our day jobs, with our big simulation type work. We did have 4 science payloads and built by different departments at West Virginia University. And so we actually finally launched last year about within a couple days of now. And on the 19th of December last year, we actually finally made our first contact, which was great. And we'd worked hard to get to that point. But the question is, now what? How do we actually efficiently and effectively operate? I mean, we were trying to develop the simulator, but now we actually have science payloads, and we have to actually work with all that and do operations. So it's not like we didn't have anything to begin with. We already were using Ball Aerospace Cosmos, as was mentioned earlier this morning. We were doing testing with this in our lab. We did development of all the command and telemetry tables. That part was already there. We already knew how we were going to hook up to Wallops to actually do the commanding through the entire comm chain. So that part was all there. So we could actually operate the satellite, you know, on a day-to-day basis, send commands up, get data down. So what didn't we have, and what kind of things did we want to add then? So as I mentioned, we're using a UHF antenna down at Wallops. It's a shared resource. We're not the only user of it. There's about a dozen CubeSats, I believe, using it. And so since it's a shared resource, they provide a schedule weekly of who gets time when. So just because we're in view of the antenna doesn't mean we get time. So we have to work through that. And then basically they come out with a spreadsheet that says when we get our time to talk. So then the other thing that we did was I kind of wanted to say, okay, well, what's that look like on a day-to-day basis and even on out days? So we came up with this homegrown tool called the Orbit InView and Power Planning tool. It's actually part of NOS Cubed. It's kind of a little piece off in the corner from the main purpose of NOS Cubed. But the idea was to generate kind of a visual view of what a schedule would look like. And so what's shown, and it's not real readable, but I'll just try to describe it. The green line represents one single day. So that's the current day. And then below that, down here, the yellow and black are indications of when we're in sun, when we're in umbra. There's actually small penumbra pieces there. So that's all based just on two-line element sets and propagating the two-line element sets. So we have that available. What was more interesting and useful for our use case is that on the lines above, we have 2 different antennas, and the one on the top here is actually for the Wallops UHF antenna location. And so we've indicated with little bars when we're going to actually be in view of Wallops. And then beyond that, once we actually understood what the spreadsheet format was going to look like, we're doing some automated parsing of the spreadsheet. And so we can indicate with different colors. So the purple color indicates that we're in view of Wallops, but we don't have a contact planned. Or the blue indicates we're in view of Wallops, and that's when they've actually assigned us time so that we can actually take a pass. And so we build up this capability, and this allows you to kind of look forward and say, okay, when are we going to have operators needed, you know, and there's not a very large group of operators, 1 or 2. And what time are the passes going to be? You know, it's a low Earth orbit, 80-some degrees. It's not sun synchronous or anything, so these times tend to wander, you know, as the days march on. So then beyond that, that kind of helps you with understanding what's going to happen tomorrow or the next day or even today. But we put together some things to actually help the operator on the current pass. So what we put together was an azimuth elevation range table. So on the left is a table, and it's just a typical ephemeris type table, time, every 15 seconds or so, azimuth elevation range. But then what we also did was we created this bullseye looking graph to display what the track's going to look like as the antenna's tracking the satellite across the sky. And so the way to read this is the horizon is the red line, okay, and zenith straight up is the very center. So it gives you an idea of your elevation. You're going up in elevation as you get closer to the center. And it also gives you an idea of azimuth. And I like to tell people, I'm used to reading maps. It's backwards from a map since it's a sky chart. So west is on the right and east is on the left. So you can get an indication of how the antenna track is going to look whenever it's actually in contact. And then what we've done is overlay in black the track as the antenna would follow it. So why? Why would you do this? Well, I mean, you've got typically times when you're going to have better comms and worse comms. When you're at a very low elevation angle, you're going further, you're going through more atmosphere, your link maybe not close. So it kind of gives you an indication of, where you are in terms of that. We also had some things we put in. We had a known RF interference source, so we colored that in red. It gives the operator kind of a visual idea as they're taking a pass, of what's going on. And so I think Matt eventually, he used this, but also just his own notes, gradually got to understand better and better when he would have good comms and when he wouldn't. So that was for the pass support stuff. So then that's kind of all on the planning side and operations side. What about post-pass type information? So in terms of that, what we ended up doing was we took the same chart that I just showed on the last page, and we overlaid it. And so what we overlaid it with was we actually knew when we sent the commands, and then we would have times from when we actually received telemetry. And so we were able to overlay the track, the black track, with colored dots to indicate some of this information. So typically when we would start a pass, and these are time tagged as well also, so you can kind of figure out, are we going north to south or south to north? So we typically send a test command at the beginning, so we have a clear data test command. And then every time we have a blue one here, that's an indication that we sent up a command to ask for data back. So we're pulling data from the satellite, our telemetry that's been stored on board. And then when you see the orange ones, those are commands just to do something, power on some switches, power on an experiment, that sort of thing. So we don't expect any response back. We're just sending a no response expected command. And then the other interesting thing is when we get the telemetry back, then in the green we've coded when we actually had a receipt of telemetry. And so you can see in some cases, we sent up a command, asked for data, got telemetry back, asked for data, got telemetry back, asked for data, okay, this apparently we weren't in a good communication geometry. We don't have any attitude control, so we're tumbling. We have a relatively omnidirectional antenna, but it's not, perfect. And so, in these cases, there's some Doppler shift stuff that has to happen that we've worked out with the ground station. So there was no telemetry received here. So it kind of gives you a graphical feel after the pass of what happened. And then the other thing we did was we actually automated this very simply with cron and at to run a few minutes after every pass, generate this data. And so we would generate the plot and then send it out to the team on Slack, so that really there was nothing anybody had to do. This information just automatically gets pushed to us. And in addition, what we did was we strip off a couple lines from some of our key telemetry points and put them out on Slack as well. And so one of the key telemetry points we look at is what's the main bus voltage of the spacecraft. And so all this gets pushed out, and so every day I can just look, or if Matt can after the pass, what's going on. So what else? What else did we have to automate? Okay, like I said, we actually have 4 science payloads on board. We're getting housekeeping telemetry down. All this is coming down in a binary format. And as it is, we don't want to send off the binary to the scientists. We want to actually give them textual versions of that. And so what we've done is set up just, again, automated jobs to post-process the pass and then generate comma-separated value spreadsheets for them of time-tagged data from their experiment and time-tagged data for all our housekeeping and so on. And then in order to automate it even further, we're sharing this. We wanted a way to automatically share this out to them. Like I said, they're not all co-located with us, so we couldn't just put it on a server, at the facility. So we're sharing it out to a Google Drive share so that they can actually get access to it. And then the final thing, this was one of the last things we kind of added in, was they would ask me, when did you run my experiment? When did you get data back from my experiment? And I said, well, okay, so I can look through the directory structure. And, it's a little cumbersome, so I wrote a script and then actually generated block type calendar views. And so on the block type calendar views, and I know it's not readable, but indicating when an experiment was run, what day it was run on, and then what day we got data back from it. So that kind of gives you an at-a-glance view, and so then you know where to look. So we're saving things off into a day-by-day directory structure, what days to look at for data for your science experiment. So again, like I said, all this was automated as well. And why? Well, kind of going back to the beginning, this is not really our main job. We tend to do simulators. We do development. We're not an operations group, nothing like that. So the idea was to offload all the things that we could. And so basically when we take a pass, our operator, Matt, or myself, or whoever else, I mean, you just need to take the pass, spend 15 minutes or half an hour, and that's it. Everything else has been automated so that we don't have to do the rest of this work. And so now a little whiplash again. So now we go back. I told you who we are, so now a little bit more about what we do. So of course, as I've been talking pretty much the whole presentation, we did SDF1. We typically do software-only simulation. And as I said, for the Class A type NASA missions. So we did NOS cubed as a companion to STF1, so you can do small satellite simulation. And then we've done simulators for human exploration, where for SLS we've taken the Artemis and Maestro that was talked about earlier, condensed it down onto a laptop, totally software-only sim. Like I said, again, the focus at IV&V is really on software IV&V, so that's really the part we're really looking at. So we want the software part, not so much, you recognize hardware is important, you're going to have to do hardware testing, but we're primarily looking at software. So we do software-only sim for that to high fidelities. And then we've brought in the exploration ground systems code and created a sim called GS2. And we've brought in Socrates from Lockheed Martin for the MPCV Orion. So we're putting together an entire HEO mission sim. And then we've also done sims for other science missions, such as James Webb Space Telescope. And again, we've condensed it all down into one virtual machine rather than racks and racks, that you would typically have. Working on the same kind of thing for WFIRST. We have a new simulator we're working on called WISP, and then are eventually going to do one for Europa and Psyche missions as well, because those are very high dollar, very important missions to NASA, and ones that the IV&V program has decided need IV&V, and we're going to work on. So with that, I'll wrap up and say thank you very much, and put a couple links down here for myself, but then if you want to know more about IV&V or the JSTAR team within that, and then some links about STF1 and NOS cubed. And finally, I'll leave you with a couple of pictures. The camera was almost an afterthought on this because it's We're really not using it for a science experiment, but we do have one on board, and we occasionally take pictures. And these are the two of the pictures we've taken. Again, they're very surreptitious because, as I said, we have no attitude control. Snap the picture, and we'll find out what we get. And so these are two of the nice ones that we've got. So with that, thank you very much.
Thank you, Mark. Any questions? Nope, guess not. Thank you. So we have a couple minutes. We're going to do a raffle, so get your raffle tickets out. We're going to do this Rubik's Cube, so I figured all these all people ought to like that. And ticket 136. Nope. 85. 97. Nope. 141. Great. And power bank. We have like a lot of stuff here. So that's from OAR, by the way. I think they donated 5 of those. So this is the third one. 68. Great. Put that back in the bag. Great. Thank you. Yeah, hey.
I had 2 takeaways. I wrote my notes and then I forget to tell them. So, I mean, obviously the one was we do simulation, but the other was, and this was more the point of the main part, you know, you're going to have to think about ops at some point if you're doing a mission. So.
All right, one more. We have the speaker here. Ticket number 65. 120. Great. Thank you. Okay. Our next speaker is Chad Loeffler. Probably screwed that up.
Chad Loeffler.
Okay, great.
From Southwest Research Institute.
Thank you.
So this is going to be a case study on 2 divisions within SWRI trying to come together and determine what should our coding standards and conventions be. So there are many reasons to have standards and conventions for projects: interoperability, portability, compatibility, consistency, reusability, readability, long-term maintenance, compatibility with static analysis tools, acceptance by customers, and reducing common mistakes. And then here's an example of why we really need standards, so it doesn't end up looking quite like this. So we did a survey between the 2 divisions in SWRI that currently do flight software mainly. And we found that many projects had their own custom standards, not necessarily external standards, and there was no consistency between the 2 divisions on which were used, just each project doing their own standard mainly. Many projects were not required by their customer to have a certain particular standard, just that we had a standard on that project, not which one it would be. Many projects found that simply being consistent to a standard also was more important than which standard in particular was being used, just as the project was consistent. And many of our projects really did not have a great way of enforcing the standard or proving to a customer that we really were following it. Standards can be checked through various means such as inspections, reviews, static analysis tools, and editors. Inspections can sometimes be infrequent, and they don't always necessarily provide 100% code coverage when done. Static analysis tools are good, but they don't always support custom standards, and not all of them integrate cleanly in the build process to be run every time there's a compile. Editors are good at sometimes supporting style and formatting checking, but not functionality and performance. And while many of our editors do have the capability of providing style and formatting guidelines or automation, many of us don't quite know how to do that within our editors. Either the editor has it disabled by default, or installing custom plugins aren't always the most straightforward way. We also found that sometimes overly restrictive standards, in the absence of good checking tools and processes, sometimes can lead to more errors than they prevent. They can also be difficult to adhere to and remember if we don't have good enforcement. And like with any tool, it can be used properly or improperly, and a standard that limits too many language features might have us using workarounds which introduce errors of their own. And regarding, say, static analysis tools or infrequent inspections, if they're only done, say, at certain milestones or at the end of a project, then that's going to lessen the likelihood that we're actually going to make substantial changes simply to adhere to that standard that we found we were non-compliant to it. And since there's always the risk of introducing errors for any particular change, and so change just to adhere to something we found at the end isn't always the best. So we said, okay, we're going to look at a couple of different standards here and see if we can figure out, okay, is there something that meets our needs and we can all agree to? So we looked at Joint Strike Fighter, C++, MISRA, Programming Research, and then two from JPL, Powers of 10, and the new one from March 2009. So we said, okay, when we're looking at these standards, they should be easy to use, understand, remember, so we can adhere to it good. They should be suitable and relevant to the applications and processes that we have. Ideally, they would have default inclusion, static analysis tools, or easy plugins for it. They'd be accepted by the industry and ideally be public domain or freely distributable and accessible. Our final two contestants ended up being both from JPL, Powers of 10, and the new standard. So for Powers of 10, there were many things that we liked about it. There were only 10 rules, which would be easy to remember. There was no licensing on it, and the code Sonar static analysis tool had support for it. But there are also disadvantages as well. It was deprecated and obsolete, replaced by the new standard. Some of the rules had significant objection by those of us at SWERI, and JPL had fixed those objections within their new standard when incorporating Powers of 10 into it. So then we looked at the new standard, and there were many things we did like about it. It fixed everything we did not like about Powers of 10. It was much more complete and comprehensive than Powers of 10, and it was created by the customer that we saw as most likely to have us required to use their standard in the future. But then for the disadvantages, there were 31 rules, and if there was opposition to saying, well, are we going to remember 10, how are we going to remember 31? It includes 89 non-public MISRA rules, and we weren't sure that there was any static analysis tool that had the 31 custom rules in it by default. So then we kind of had a philosophical divide between going for external standards or going for internal standards. And if we had an external standard, would we follow it 100% or take only pieces of it, thus creating an internal standard? So for external standards, there are many advantages. It's already been created by somebody else, so we're not reinventing something. It's accepted by the industry, and it's being developed and maintained by somebody else, so we're not expending our resources on it. There can be provable compliance through enforcement, such as static analysis tools and plugins to editors and IDEs. Our primary customer is NASA and JPL, so if we pick their standard, then it's probably going to make them happy for that. But then there are disadvantages to external standards as well. They're developed for another organization's applications, processes, and needs, not necessarily our own. They may be too restrictive in certain areas or even already deprecated in certain cases. They may not always be publicly available. It may be a standard that we are begrudgingly accepting as opposed to something that we've agreed is going to be of great benefit to us. Not all of our customers are JPL, so just choosing a JPL standard does not guarantee all of our other customers are going to be happy with what we've chosen. So then we looked at internal standards. Okay, if we have an internal standard, it's custom created to identify and address all of our needs. It'll fit in well with our processes and our applications. And there's a better chance of it being accepted internally because it's one that we've created ourselves and have gotten buy-in from everybody on. But there are disadvantages as well. We may not have the ability to enforce it because we may not be able to configure our editors to support a custom internal standard, nor would we really ever be able to find a static analysis tool to support our internal standards either. They may not be acceptable by our customers, and if we have the ability to freely change our standard, then we're likely going to always be changing it and modifying it. And if there are already in standards in existence right now, are we benefiting by adding yet another standard to that list already? So where we've ended up right now is it's still an ongoing process between the two SPRI divisions, and I'm going to have to leave this with a cliffhanger and maybe a part 2 next year on which standard we've actually chosen and why. And so I've added a couple of extra slides here in terms of we've looked at other languages too, such as Python, TCL, and Java, and we've not formally chosen a standard yet, but for reference, I've included some up here. Python's PEP 8. It's an external standard by the owners of the language, and it's created, maintained, and updated as the language evolves. There is one for, I should say, that we use Python heavily with our GSE equipment, GSUS in particular. TCL is gaining a lot of traction with us since it's used by the Giromon tool, and so we can do a lot of board checkout with TCL as opposed to having onboard software on the board. And there is a TCL standard in existence for it. And then Java is used in a lot of our ground processing software and applications. And there are guides from Oracle, although that one's deprecated now. There is a Google style guide and one from JPL as well. And then there are also some pretty good notes that I've shown here from the Python's PEP 8 guideline. So a style guide is about consistency, and consistency is important within a project, but it's even more important to be consistent within modules and functions within that project. Also, there are times when you may want to be inconsistent. Do not break backwards compatibility just to be in compliance with the new standard that was not in effect when the software was written. And some reasons to perhaps ignore standard is when applying that standard would make it less readable. If that would then make it inconsistent with everything else within that particular function or file, there's always the trade-off of if we adopt a standard, do we go back and refactor and retrofit everything in existence, or do we have some threshold as far as, okay, if we're going to make a major modification, then we have it comply. Otherwise, if there's no other reason to change it, then there's the possibility of introducing an error into it when we do that. Okay, are there any questions? Yes?
I had a general comment because I've worked with the JPL standards that you listed there, and just as you're working through your investigation, keep in mind that C and C++ are not necessarily going to fit some of those standards that are listed for C. And as a use case, last year we ran our project that was built for JPL in C++ 11, ran it through their static analyzers, something like 500 odd errors, and we're looking at it like we cannot be that wrong. And it turns out that their static analyzers didn't even know about their rules. They thought they did, but it didn't even know how to deal with C++ 11. And out of 500 some odd errors, basically one rule actually tripped, which was you shouldn't have more than 60 lines in a method. So take it with a grain of salt that, you know, those rules are going to fit your language. So if you're really working with just C, fantastic. But if you're working with C++, take a look at them and see how they're going to apply. And then there's also some couple ambiguities there with the term of initialization as well that we kind of asked around and got various answers. So that also becomes a project dependent requirement. So.
Thank you very much. That's a lot of good information and good things to think about.
Other questions? I don't see anybody. Okay, great. Oh, another one? Oh.
We were wondering what tools and technologies have you tripped over in actually checking all the rules? Things like LDRA or plugins for IDs and whatnot.
So right now, within my particular division and my particular group, we've used the PC-Lin static analysis tool, which has been quite great. But we've also found generally with static analysis tools that there can be many false positives. And if we don't run the linting tools right when we start writing the software and we do it at the end, there's sometimes overload with thousands of warning messages. And so we've almost been training ourselves now. So we've managed to get PC-Lin to integrate with our build process. So if there's an error, it's not even going to compile. And so we've trained ourselves almost to write to it and the miserables as we've turned on within it.
Okay, thanks.
Other questions? Yep, sure.
Something probably not in your survey that I've experienced is when creating an internal standard with a panel, some people are willing to die to make sure that the curly brace goes along with the function definition or the line below. So it's a big waste of time. I'm a proponent for finding a standard, accepting it, and maybe tailoring it. But just a little comment there.
I agree. Yes, internally we all have, it can be very easy for everybody to divide into certain camps as to whether, even with spacing, is it 2 spaces, 3 spaces, 4 spaces to replace a tab? Yes.
Okay, thank you. Oh, another one?
You made the point before that it's more important to have a standard. How long have you been debating, and how much longer is the debate going to go on before you simply pick one and say, this is what we're doing, and we have one now?
Very good question. So I'll answer that in 2 parts. So the other division, not mine, in the past they ran their survey and their attempt, I think, it was a couple of years ago, I don't remember exactly when. And I've also heard from those who've been there longer than me that this is not the first time the divisions have tried to come up with a standard everybody could accept, and each time when they've gone down the path of going for an external standard and requiring 100% buy-in, it's always become an abandoned process. So we're hoping that this time we're going to get it right, whichever way it ends up falling out. We started this process probably 6 months ago, and so when I wrote my abstract, I thought we'd be much further along and I'd have much more to present at this point. And so we ended up hitting such a brick wall on the external standard functionality and performance, we've now gone towards style and formatting internal standards for at this point.
So just a quick comment for the standards. If you look at the introductions and front material for the standards like MISRA, AutoSAR, JSF++, they all call out that they applied only to a specific version of the language. So that's also something that should be taken into account. For instance, MISRA C++ only applies to C++ 03. And they do not account for modern C++, whereas AutoSAR C++ for the automotive industry is taking that into account, and it's actually evolving. You'll see they've taken over in the evolution of MISRA as well. So there's some things happening for the external standards that you should take into account. And keep in mind the external committees are actually doing a lot of work to make sure they keep in sync with the evolution of the languages themselves.
Very good points.
Lots of good questions and comments. Anybody else? Okay, great. Thank you. Great. Yep. Next presenter is Daniel Hellstrom.
Hi, my name is Daniel Hellström from Cobham Geisler. Earlier this week I had a presentation about our new processor IPs and the roadmap going forward. This presentation, as part of the sponsorship, I will talk a bit about the current components processors and some announcements recently made around them and the software environment updates for those components. Yeah, that's pretty much it. So our current high-performance processor is the GR740, which is a quad-core Leon 4 machine running at 250 megahertz. We just recently announced that we are signed a contract with ESA, and together with RUAG Space, we will design a new single-board computer based on the 740. It will include an FPGA, and that will sit next to it, and it will be a flight model, and we will also develop boot software for it, and it will have most probably a VPX backplane. So you can read more about that on our homepage. Recently, we finished our core activity we had at ESA previous 2.5 years, I think. That resulted in a single-board computer that will be available next quarter, also based on 740, and it has been used together with a mezzanine board interfacing a European FPGA that is SRAM based, so it's possible to reprogram it in flight. And we also did some boot software for that one. We also, last week, we had a press release on GR740 will be available in plastic. So that's another ESA activity, also funded by other than ESA. And basically we take the 740 die as it is and put it into a plastic ball grid array. Same number of pins basically as the 740. We expect prototypes to be available after summer. Going through the 740 project, at the moment we're starting the qualification, and we plan to have a QML equivalent in Q2 and Q3, and after that we'll seek DLA approval for QML V. I'll skip those. GR716, I presented that last year, I think, at Flight Software Workshop, so I won't go into detail of that one, but it's a Leon 3, a new bus architecture, and on-chip memory. It's our new microcontroller. And then we made that available this year. So, and there's development boards and prototypes available. You can find on the homepage more information about it. We are taking that into qualification, and it's expected to be available in a year. So this is basically the features of the 716 as it is today. We are currently working on an enhanced version, which will be a 716B. The primary updates will be a new floating point unit that will use the floating point unit that we have in our other components, which are more, it's pipelined, so it's faster. We will double the frequency. We will have a spaceway router with 2 ports instead. There's a new IP that allows CAN-FD. There's a new Ethernet support in it, and we also increased the resolution significantly on the internal ADC. But there's also a new mode where, well, the processor will still be available for you to program, but it also features interface to SRAM-based Xilinx FPGAs. And it's a new IP that we are currently developing and testing. So you can interface it, for example, to Vertex 5 or Altuscale. And then it can be used to be to program the FPGA or to scrub the FPGA in runtime, so that you can use those FPGAs in space easier. And the schedule for this one goes faster than the 716 because it's based on an existing product that we already taken through the flow. We are just adding some new features to it. So we expect tape out in June and to have prototypes after the summer next year. On software, I think last year or maybe even maybe the year before that, I've been here and talking about our bootloader that we made for the JUICE satellite mission at ESA, where 7 of those instruments are using our bootloader. We have had another activity, Cora, which I just mentioned, also using that bootloader. And now the new 740 single board computer that will be reused and target flight as well. Even though there's no specific mission, it's intended to be in many different missions. So in parallel with all that development, we have internally also worked on making it a product. So GR Boot was released a couple of months ago. You can find out more on our homepage, but the difference to the JUICE bootloader we had from the start is that now we can run it under different processor components. There's a new software architecture that allows BSP more easy, and there's the standby monitor that we had. It acted as a remote terminal over SpaceWire, so you could patch and upload new application. That's not currently available, but it will be when we're done with this. So in a half a year, that will also be available. About that bootloader, it's following the ESA Savoir flight computer initialization sequence standard, and also we have developed that using the ESSS engineering and quality standards. It's capable of initialization of the whole system, and it performs self-tests, and then it generates a boot report for the application to read later on. It is then you come to an optional, if you want to add your own standby, or later on you could plug in our SpaceWire remote terminal. Otherwise it goes directly into application loading. There's a ELF-like format that allows you to patch afterwards, and it uploads section by section to different parts of memory, if you like. And it's capable of booting all the operating systems that we support today. So the two use cases we see is just operated as an ordinary bootloader, but it has a fallback. If an image fails, then it will go to the second fallback image. But you can also use it, a bootloader, with maintenance mode. Along with that, we deliver it with test documentation and validation cases that we use our simulator to run it on. We also recently released TSIM3, which is available for beta testing for existing TSIM2 customers and GRSIM customers. It supports multi-core. That's the main feature of TSIM3. So now you can run Artem's SMP, for example, in the simulator. And if you compare this to the simulator to QEMU or SIMIX, that has also been discussed through the week, is that we our simulator has a high precision multi-core model of the CPU and the bus, which allows us to model bus contention and interprocessor conflicts. Also new is we have now an SDRAM model. There's a Tickle front end, so we have tried to harmonize GRMON and the TSIM's user interface. So you will, if you're a GRMON user, you will recognize yourself much easier to get started with TSIM. And the Tickle interface allow you to integrate TSIM into various frameworks or perform validation checks of your software without writing software for it, just to do that in Tickle instead, and so on. And there's also GDB 8 support now. Well, and there's a bus trace, there's a lot of things going on. In a couple of weeks, we will also release support for the Leon 4 740. The first release will focus on the bus architecture, the L2 cache, and the memory, and the CPU itself. Not so much the I/O. And we have focused on the primary use case, where we have the 64-bit SDRAM and the default settings in the L2 cache when it comes to replacement policies and so on. And we have the wider bus width. But we also added some new IPs like GR CAN interface, for example. But then we also plan another release in the beginning of next year, where we will add unbus split support. We already done part of that work in the CPU. So then we will also have a more timing accurate models that actually, even in the 740 with the HB split responses, it will be able to model that and give correct timing. And the roadmap for TSIM3, I can mention, there's a lot of things that we plan, but fault tolerance and error injection is one of them for next year. And also to configure it in 32-bit SDRAM mode. This is my last slide. There's some other updates on the software environment that I want to mention. We have worked quite much with the LLVM support throughout the last 2 years. We have had 3 different ESA activities on it, and we've invested some time ourselves, of course. So last year, I think I presented that on Flight Software Workshop, and now we have. It's not based on on the master branch of LLVM, but now it's on a stable branch, version 8. So we undergone all the testing, and we also added the UT700 support this year, and some additional optimizations from when I presented last year. So we now consider that as ready for production. We compare that with GCC, and we find out that it's basically the same performance. So it's more application dependent than it is compiler dependent, which performance you get, if it's better with GCC or LLVM. We also have introduced GDB 8 support in all our tools, which means that we can get better C and C++ source level debugging. So we're now updated all our environments, both BCC and Artems. I think we released that last week, and then VxWorks, the latest version of VxWorks 7, to include the new LLVM Clang compiler, and it's now also built using the newer dwarf format that allows us to take benefit of GDB 8. So that's pretty much it. Thank you for listening.
Have any questions? No questions? All right. Okay. Thank you, Daniel.
If you have any questions later on, I'll be in the booth. So.
Yep, and they're right out here.
Yep.
Yes, in the hallway.
Okay, thanks.
So we have a few minutes. So before lunch, we have more things to give away. No free beer, though. sorry, no free. That's tonight. MathWorks t-shirt, it's, I think it's a large. Let me look. Yep, it's a large. So, 92? $89? $73? $70? I could just actually just start calling off numbers like 70, 71, 72. 90? 95? 95, way! You're welcome. And Concurrent gave us some stuff this morning. So we'll do this. This has a t-shirt and a coffee mug, and I won't even look at the, well, it looks like, oh, this is an extra large, so anyway, we might have a different size in here. If you get it, we can probably trade you. 18? If that size isn't good, let me know, and we'll see what we can find. Great, thanks. That's it, so we get to early break for lunch. We'll be back here at 1 o'clock. Reminder, I'm not sure if I said this earlier, if you're for dinner tonight, 6:30, cafeteria is right across the hall here. Bring your badge to let you in. If you don't bring your badge, that's okay. We'll have a sheet there. It'll just be faster to get in if you have your badge. Thank you.